Hey, Doovid here. We are live. Glad to be back. Been meaning to get to a lot of these streams, poured my research on the multiple truth hypothesis. I'd been doing a whole bunch of chess studies recently for that is also going to be related to the multiple truth hypothesis. And I guess, Doovid's a chess player and chess coach and likes the chess studies to understand cognitive processes. And then I saw the news this week about AlphaFold, the same engine that was used for AlphaZero chess and AlphaGo has supposedly solved this great protein folding program. So one of the pillars of the multiple truth hypothesis is this concept called truth discovery, which is basically an algorithm that's programmed into computers to search after truth in a formulaic, algorithmic way. And we're going to look at some of those formulas, and they're actually extremely complicated mathematics. But from a certain perspective, like AlphaZero, that at least was the best computer program out there, only really has a few hundred lines of code. It's not extremely complicated coding, and it's more a mathematical algorithm. And these are somewhat complicated, and then it takes the computer to be able to process these algorithms. But generally, you could set a goal to the computer, like solve chess, win for white, checkmate the black king, vice versa, and allow the computer, through the process of trial and error, to determine the best path. And it's also going to be related to cognition and neuroscience. And I have a whole bunch of articles that I'm going to go over showing the comparisons between the likely explanations for the hard problem of consciousness and how the brain works, and machine learning neural net algorithms that are currently solving the most difficult problems in the world, like protein folding. And you also possibly from an interfaith perspective. So the original origins of the multiple truth hypothesis is essentially spiritual, trying to make sense of systems that have conflicting axioms to remain still true, or the logical implications of having various systems with contradicting axioms that have different conclusions based on those axioms that lead to direct conflict, as possibly could be seen in world affairs and conflict between humans, but from a problem-solving level to work with a greater system that allows for that. So that that was the origins of my desire for the multiple truth hypothesis, and general Talmudic pill pull, but also largely my knowledge from artificial intelligence coming from chess and trying to keep up with the latest engines and news, and reading books I have right behind me. The New in Chess Game Changer, about AlphaZero's groundbreaking chess strategies and the promise of AI. I didn't even finish it. Almost finished it. But, I keep up with these things. It's been interesting. I've been talking about it. And generally, chess AI is not really that interesting to people. People don't really care about it besides chess players or computer programmers. It's the practical problems that AI might solve that people care about, like AlphaFold. Can we cure coronavirus? Can you set the challenges to the greatest problems to the computer and have the computer solve it for us? So let's look at some of these papers. Let's see what AlphaFold is. Let's look at the paper they published and what they claim they actually have done and the greater implications. And then I'll go through a little history of AlphaZero from a scientific level of the machine learning algorithms, the main terminology. Some of this is a lesson for me myself, just to read through these papers so I could express these things in the more proper terminology. You see me twisting my own tongue. Some of this terminology is extremely complicated. So I'm going to read through some of these papers. What's a neural net? And what are the implications and the similarities between neural nets and neuroscience and artificial intelligence and the hard problem of consciousness. So a few papers. I have a paper on that I'm going to read through, and then I have some slides on machine learning, reinforcement learning, and the terminology for this. So I'm just going to enter a screen share. We'll look at a few things, and hopefully this video will be interesting to some people. And I looked online. Like Lex Friedman had coverage. Lex Friedman, MIT professor, did a video on it. DeepMind solves protein folding, but not that much stuff on it. So you'll see a few articles in periodic journals. Even AlphaFold, I'm not even sure if it's a major news story. So here you have DeepMind publishing it, Nature, Vox, Guardian, CNBC, Science. So most people haven't heard about this. They didn't. If you're more technical, more market oriented, this is extremely important in the future of science, and I'll try to explain it. And it's also likely to be a cornerstone of this multiple truth hypothesis I keep on talking about. So here, just Wikipedia. Let's start. What is AlphaFold? AlphaFold is an artificial intelligence program developed by Google's DeepMind, which performs predictions of protein structure. The program is designed as a deep learning system that is built to predict folded protein structures to the width of an atom. November 2020, a version of the program titled AlphaFold 2 took part in the 14th edition of the biennial critical assessment of techniques for protein structure prediction competition, in which it achieved a level of accuracy much higher than any other computational method. The program scored above 90 for around 2/3 of the proteins in the CAPS global distance test, a test that measures the degree to which the computational program predicted structure similar to the lab experiment determined structure, with 100 being an exact match. So you see it had 80-90% accuracy in predicting the folding of proteins. You have a long chain, polypeptide chain, and it folds over into these interesting three-dimensional structures. And these structures are probably determinative, that in the end, like a 3D molecular representation of what the structure looks like is likely largely determinative from the genetic code and the laws of entropy in physics and energy reduction, that it's eventually going to reach this state, although there's obviously a large amount of uncertainty in the patterns. So it's pretty complicated to predict these patterns, very complicated even just to discover these patterns, and saying if they're common patterns like in COVID-19, the SARS coronavirus, what is its protein structure, versus predicting that from a sequence. So impressive result. And here's their official page. The DeepMind page. Which I've shown DeepMind before, and I'm going to read more articles about it, because DeepMind is not that old, only like 10 years old, but it's purchased by Google. and it's what produced AlphaGo and AlphaZero, and now it's producing things that are more scientific geared, not to just like solving a game like chess, but to solving real world puzzles, which in reality has more implications than just the game of chess. Chess might be an interesting game that's even played by 20% of humanity, but the creators of the program are really more interested in these practical results and saying this is stuff that's economically profitable, benefits people, all the various things. So here's their published article from last week, November 30th, Solution to the 50-Year-Old Grand Challenge of Biology. DeepMind produced a solution for this, having worked personally on the problem for so long, and after so many stops and starts, wondering if we'd ever get there, is a very special moment. So 50 years, and so I'm not going to go over too much what protein folding is and why it's a problem and how exactly the algorithms of AlphaFold went about solving it. But when I go over how that works for chess, you'll see it's the exact same mechanism that the AlphaZero program used for solving AlphaFold and will use for probably countless other problems in the future, and theoretically would work if it went after what is the truth, what is the meaning of everything, what is the answer to all questions, so to say, from the multiple truth theoretical hypothesis perspective, that what if you programmed AlphaZero to solve all the problems of the universe, the meaning of life, so on and so on. So here you see their accuracy, and you see that no one had ever broke 50% before. And the AlphaFold first attempted in 2018 did over 50%, 2020 over 80%, and you'll see the mathematics behind how high that could get, if that could get to close to 100%, or if there's so much uncertainty that even AlphaZero will have a capped prediction rate. So we're not going to get too much into the biophysics here of what does it mean to predict a protein structure. You see the comparison with the green and the blue and the overlap of the predicted and the experimental results. So here is the diagram you saw on Wikipedia. It's an overview of the main neural network model architecture. The model operates over evolutionary related protein sequences as well as amino acid residue pairs, iteratively passing information between both representations to generate a structure. So the program has the protein sequence, and then there's a genetic search and embed, but also the possibility for other embedding. And then there's an MSA assemble of residuals in sequences from the main sequence. And so, and you also have a confidence score. I'm going to go over this stuff related to chess, which historically this program was designed for chess. But just see this, and when we look at the chess, you'll see the similarities in the machine learning neural networks that here they're claiming it's a once-in-a-generation advanced predicting protein structures with incredible speed and precision. The leap forward demonstrates how computational methods are poised to transform research in biology and hold much promise for accelerating the drug discovery process, and possibly even to curing COVID-19. Okay, so with that, let's talk about how these algorithms actually work. Oh, so Mr. Thomas Sherman, I appreciate you joining in the chat. Yeah, this man had sent me this book. So I have here Pathology, The Nature and Origin of Beliefs. And I guess this man saw me on the Charles Moskowitz show, and I read through it. It's very interesting. And, it's about the foundation of beliefs in the mind, first principles, subjective, objective beliefs, science, language, dialectic, principles of interference and logic, secondary criteria, objective truth, science and objectivity, honesty and reality, beliefs of the heart, beliefs of the spirit, action and purpose, good morals, and a little more. So hopefully at some point, Mr. Sherman will join me and we'll actually discuss this. So it said multiple truth hypothesis emerges largely from interfaith and working with various people from religious backgrounds. You see Doooovid's YouTube. This is what I created my YouTube page for, was to record these events. That's originally the very first. Here you see the big interfaith. I still have the Temple Bethel where I had my bar mitzvah, the big World Sabbath event there. We had Jains and Sikhs and Hindus and various denominations of Christianity, and so on all together. And for years I've been doing interfaiths and just listening to people express, besides the Hindu Hare Krishna ISKCON stuff that I do more frequently, or am more directly involved with, there's plenty of interfaith programs that was the precipice for me trying to come up with the multiple truth hypothesis. So if just Judaism, Christianity, and Islam, like Judaism says that Abraham sacrificed Isaac, almost, and before God stopped him. Islam said it was Ishmael. So it's one of these truth values. Can only one of them is likely to be true, and the other false, or both false, or it's possible that you could come up with some method and claim that they're both true. Let alone bigger contradictions like in cosmology, like young Earth creationism versus old Earth creationism. Was the world created in 7 days with the flood, and or it was a Hindu cosmology that somehow we descended from spiritual forces from the gods, or all the various cosmologies, scientific, and to at least give them some credibility, or allow that you could accept that they're based on certain axioms, because the multiple truth hypothesis is postulating that truth is really something much more complicated than is beyond the perception level of humans. So is it, what is the real truth? What we understand to be the truth is not likely to be what the truth is in actuality, and that could actually be scientifically demonstrated with just basic physics, where what we see is not really what we think is out there based on the science. We have a mental representation, and the multiple truth hypothesis is designed to take the various axioms of different systems and give you an output comparatively of values, hopefully numeric, that this would even be like a computer program and something that could have exact numeric values. And I'm going to show you how that's possible. Let alone you'd have to have a whole team of programmers. And conceptually, what I'm saying regarding AlphaFold is not possible yet, where the computer is able to solve a problem like protein folding in a singular problem, or play better chess than other programs, versus a straight function that the computer would be set to say, discover the answer to all the world's problems. What is the meaning of life? Could you create an algorithm to program the computer? And so science fiction has already thought about these things, and from a mathematical perspective, at least, what are these equations that AlphaZero is currently, what's the method that's currently being used, versus theoretically what is possible, and how do you understand truth from just in the maximum amount of human knowledge? All of human knowledge put together has a certain maximum, and beyond that maximum, truth exists. And to summate, or a computer at least collectively, because humans are, we could talk spiritually, but we reside in different bodies and have different minds, And there's not necessarily, without coming on to spirituality and esotericism, an easy way for collectively all the minds of humanity to merge and work towards one problem in a way that computers could. And hence, more and more society gets turned over to computers. I did my stream on UBI. You could check my previous streams on automation and UBI, where I go over some of these things and how these machine learning algorithms are really going to pop up into every aspect of our life going forward with technology. Although, God forbid, there could be war, there could be horrible things that happen, and there could be calamity that doesn't allow that to happen. In fact, Dr. Edward Dutton was mentioning, the reverse Flynn effect, where IQ and intelligence is decreasing. And in all likelihood, the people who are building these machines now, that the generation later won't be intelligent enough to operate these machines. And I might invite John Frances Greppi back actually to help understand this AlphaFold if he has any expertise in protein folding. But you just try to add together these various things to a full scientific understanding of how this also applies to the actual science of understanding how the material world works, and the computer algorithms hinting towards what the truth is. And we can see our minds, the best of human knowledge, what that was hinting towards, like chess. And I'm going to be talking a lot about chess, not that much today, but like the best players in the world understood chess in a certain way, but the computer was better and looked at chess. What does it mean that the computer looked like chess, but had a style of chess that was different than the top players? And generally today, top players have at least integrated or even mimic and copy the method of the computer, because the method of the computer is obviously superior. So we're reaching the point where AlphaFold did not solve the problem of protein folding. AlphaFold created a computer algorithm that is capable of making predictions that are largely accurate, largely due to statistical methods. And so saying that's not really solving a problem. It's a statistical method that is quite accurate and possibly could eventually be a statistical method that is nearly accurate, like chess. AlphaZero did not solve chess, even though obviously AlphaZero understands chess exponentially better than the top humans and probably all the top humans combined knowledge put together. But that's not a solution. It's a statistical method designed to put us towards a better understanding. And so with that, I'm going to go through a whole bunch of stuff. I find it interesting. I'm, even just for my own sake and, my method, because, multiple truth hypothesis is also going to be a method, like a method for chess players, like a memory technique. They try to demonstrate multiple truth hypothesis works. And I could prove that as a mental technique on the chessboard. But in the way that a person in one mind could have multiple conflicting things going on at the same time, because you don't have to have dissonance from conflict. So this is going to be somewhat complicated. And I've talked about cognitive dissonance before, but generally cognitive dissonance is because there's a dissonance between the way a person views the world and the way the world actually is. And you have to create a template through which to view the world. In order to view the world, you need predictions that have already been made to build larger predictions off of. But the problem is a lot of those early predictions are going to be incorrect and cause a person dissonance because they're operating inefficiently in the world because they have incorrect axioms. And so most of the models for the hard problem of consciousness, conscious models, we're going to look at it, are similar to machine learning models. So as a mental technique, just saying that you could have conflicting models in your head is going to cause you some dissonance. You might need a technique to limit the dissonance. But it's say like you could play the Queen's Gambit and the King's Gambit. You don't have to be limited to one. You could understand in different variations. A person might have a natural proclivity towards one model or another, but a person could operate different models. It's like a person could convert to Judaism. A person, could have been a Christian or a Muslim and become a Jew, or any of the various permutations. A person could grow up in one culture, one language, and switch to another. The mind is unquestionably capable of these things, but it causes dissonance. So one of the best ways of creating a template to understand is just to read these papers. So I have some PowerPoints also, but in terms of the greater mental technique of the multiple truth hypothesis, yes, there is a benefit to just reading what you want to understand and then listening to it back, and having the words that leave your mouth. And it's also somewhat based on like a Talmudic religious technique, and the chunking might explain it. Like I've read even papers about the efficiency of mantras, but say even if nobody watched this, just the value to me myself of reading these papers and listening back. Just the chat, James, tell me the most influential, powerful family in the world is. You mean like the family of David, King David, and his descendants? I mean, I'd say the family of Adam. Talmud clearly says we're all descended from the same family, the essential human nature, the universal brotherhood of man. The axiom being that we have one Father, that's the Father of everybody. So it's axiomatic in that way that all people are equal because we're all from the same family. And if you don't accept the biblical model, the different models would have different axioms that may not imply equality. So within the universal brotherhood of man, there might be factions that are more powerful than others. But even say like King David and the descendants, probably not actually a powerful family, because it's probably an improper way to look at it. But within the multiple truth hypothesis model, you could set that as axioms to converse by and make predictions. And so even Baptist Christians and Muslims worship the God of the Jews. And for interfaith, the purposes of the multiple truth hypothesis is breaking down axioms to the conclusions of those axioms and the predictions that they make. And so the similarities between Christianity, Islam, and Judaism, and the various different predictions that those systems would make, and a comparative analysis. So in theory, and even if you're looking, say Rockefeller, Rothschilds, Warburgs, Wallenbergs, Morgans, in that system also, like, yes, there's conflict and there's harmony, because you have multiple systems that are operating up against each other or in correspondence, harmony with each other. And that might be able to be predicted based on axioms. And from a business level, you could look, like all those various families. And so, okay, so I want to go on and just start reading these papers and get a better understanding for what is this technology, what is AlphaZero, and I have some slides. So let's look first at this. Tim Wheeler has a blog on. He's a chess player, but AlphaGo Zero, how and why it works, is already back from 2017, but good enough, and it makes the definitions. It has some nice diagrams, and this one mostly works with tic-tac-toe. We'll show the basic understanding of tic-tac-toe, which has about 250,000 total permutations and could be solved with 3 simple rules. DeepMind's AlphaGo made waves when it became the first AI to beat a top human Go player in March of 2016. The version of AlphaGo, AlphaGo Lee, used a large set of Go games from the best players in the world during its training processes. A new paper was released a few days ago detailing the new neural net AlphaGo 0 that does not need humans to show it how to play Go. Not only does it outperform all previous Go players, human or machine, it does so after only 3 days of training time. This article will explain how and why it works. Monte Carlo tree search. And I took Monte Carlo tree search in university in the Tishman School of Construction Management in civil engineering related to scheduling. But Monte Carlo tree search is an extremely common statistical method, probably most famous for casino gaming. That's why hence called Monte Carlo tree search. The go-to algorithm for writing bots to play discrete deterministic games with perfect information is Monte Carlo tree search. A bot playing a game like Go, chess, or checkers can figure out what move it should make by training them all, then checking all possible responses by the opponent, all possible moves after that. For a game like Go, the number of moves to try grows really fast. Monte Carlo tree search will selectively try moves based on how good it thinks they are, thereby focusing its effort on moves that are most likely to happen. Discrete, deterministic games with perfect information, where both players see everything, players competing against one another, every move has a set outcome, individual, separate, and distinct moves and positions. More technically, the algorithm works as follows. The game in progress is in an initial state, and it's the bot's turn to play. The bot can choose from a set of actions. Monte Carlo tree search begins with a tree consisting of a single node for the node is expanded by training every action and constructing a corresponding child node after each action. Below we show the expansion for a game of tic-tac-toe. So if you had this position S0 with the two blue X's on a corner in the center and the two red O's on those corners, that leaves the X's with 5 different moves, possibilities. So the value of each new child node must then be determined. The game in the child node is rolled out by randomly taking moves from the child state until a win or loss or tie is reached. Wins are scored at, losses at, and ties at. So you had 5 different possibilities that X could play from S0, and then you want a numerical estimate of how likely blue or red, X or O is to win. And it does that through basically a rollout. Like if you play backgammon or Monte Carlo, just by rolling it out, let's just do it again and again and again and calculate how many of those turn into wins. The random rollout for the first child given above estimates a value. This value may not represent optimal play. It can vary based on how the rollout progresses. One can run rollouts unintelligently, drawing moves uniformly at random. One could often do better by following a better, though still typically random strategy, or best estimating the value of the state directly. More on that later. Above we show the expanded tree with appropriate values for each child node. Note that we store 2 properties, the accumulated value and the number of times rollouts have been run at or below that node. We have only visited each node once. The information from the child node is then propagated back up the tree by increasing the parent value and visit count, it accumulated value, and the set of total accumulated values of its children. So now the n here is 5, and w here is -1, which is the sum of the 5 different nodes. Monte Carlo tree search continues for multiple iterations, consisting of selecting a node, expanding it, and propagating back up the new information. Expansion and propagation have already been covered. Monte Carlo tree search does not expand all leaf nodes, as that would be very expensive. Instead, the selection process chooses nodes that strike a balance between being lucrative, having high estimated values, and being relatively unexplored, having low visit counts. A leaf node is selected by traversing down the tree from the root node, always choosing the child with the highest upper confidence tree, UTC score. UCT score, upper confidence tree. Where is the accumulated value of the X child is the visit count for the X child and is the number of visit counts for the parent node. The parameter control the trade-off between choosing lucrative nodes and exploring nodes with low visit counts. It is often set empirically. The UCT scores for a tic-tac-toe tree are as follows. So the different moves. In case you pick the first node in the event of a tie, one can either randomly break the tie or just pick the first of the bet nodes. The node is expanded and the values are propagated back up. So from the first branch, now there's 4 possible moves in return that O could make. Note that each accumulated value reflects whether X won or lost. During the selection, we keep track of whether it's an X or an O's turn to move and flip the sign whenever it's an O's turn. We continue to run iterations of Monte Carlo tree search until we run out of time. The tree is gradually expanded, and we hopefully explore the possible moves, identify the best move to take. The bot then actually makes a move in the original real game by picking the child node with the highest number of visits. For example, if the top of our tree looked like this, where you have 256 visits, and the first one had 106 of them, then the bot would choose the first action and proceed to. And that means that the bot spent the most time making calculations within the first iteration. Efficiency through expert policies. Games like chess and Go have very large branching factors. In a given game state, there are many possible actions to take, making it very difficult to adequately explore the future game states. As a result, there are estimated board states in chess and Go played on traditional board has around. Might be a typo there, but there's near infinite possible variations of chess and Go. I mean, it's not infinite, but it's like 10 to the 100th. And we look more into that at a different time. More evaluation with vanilla Monte Carlo tree search just isn't efficient enough. We need a way to focus our attention to worthwhile moves. Suppose we have an expert policy that for a given state tells us how likely an expert level player is to make each possible move. For the tic-tac-toe example, this might look the probability of making the first move is 90%. Probability for the second, third, fourth, fifth move are just a few percent. If the expert policy is really good, then we can produce a strong bot by directly drawing our next action according to the probabilities produced by, or better yet, by taking the move with the highest probability. Unfortunately, getting expert policy is difficult, and verifying that one's policy is optimal is difficult as well. Fortunately, one can improve on policy by using a modified form of Monte Carlo tree search. This version will also store the probability of each node according to the policy, and this probability is used to adjust the node's score during selection. The probabilistic upper confidence tree score used by DeepMind is, there's supposed to be an equation here, and I guess the problem with his blog doesn't have it. As before, the score trades off between nodes that consistently produce high scores and nodes that are unexplored. Now node exploration is guided by the expert policy, biasing exploration towards moves an expert policy considers likely. If the expert policy is truly good, then Monte Carlo tree search efficiently focuses on good evolutions of the game state. If the expert policy is poor, then Monte Carlo tree search may focus on bad evolutions of the game state. Either way, in the limit, as the number of samples gets large, the value of a node is dominated by the win-loss ratio as before. Sufficiency through value approximation. Second form of efficiency can be achieved by avoiding expensive and potentially inaccurate random rollouts. One option is to use an expert policy from the previous section to guide the random rollout. If the policy is good, then the rollout should reflect more realistic expert-level game progressions and thus more reliably estimate the state's value. Second option is to avoid rollouts altogether and directly approximate the value of a state with value approximator function. The function takes a state and directly computes a value without conducting rollouts. Clearly, if the value is a good approximation of the true value, it could be executed faster than a rollout, and time could be saved without sacrificing performance. Value approximation could be used in tandem with expert policy to speed up Monte Carlo tree search. A serious concern remains, how does one obtain an expert policy in value function? Does an algorithm exist for training the expert policy in value function? AlphaZero neural net. The AlphaZero algorithm produces better and better expert policies and value functions over time by playing games against itself with accelerated Monte Carlo tree search. The expert policy and the approximate value function are both represented by deep neural networks. In fact, to increase efficiency, AlphaZero uses one neural network that takes in the game state and produces both the probabilities over the next move and the approximate state values. Technically, it takes the previous 8 game states and an indicator telling it whose turn it is. Leaves in the search tree are expanded by evaluating them with the neural network. Each child is initialized with corresponding to the prediction from the network. The value of the expanded node is set to the predicted value, and the value is then backed up the tree. Selections and backup are unchanged. Simply put, during backup, a parent's visit counts are incremented and its value is increased according to. The tree search follows another selection, expansion, and backup step. The core idea of AlphaZero algorithm is that the predictions of the neural network can be improved, and the play generated by Monte Carlo tree search can be used to provide the training data. The policy portion of the neural network is improved by training the predicted probabilities for the match, the improved probability obtained from running Monte Carlo tree. After running Monte Carlo tree search, the improved policy prediction. So it's for a constant, and I'll show you these equations in a different paper. Values of close to zero produce policies that choose the best move according to the Monte Carlo tree search evaluation. The value portion of the neural network is improved by training the predicted value to match the eventual win-loss tie result of the game. We have the value loss, the policy loss, extra regularization term with parameter and represents the parameters of the neural network. Training does entirely in self-play. One starts with a randomly initialized set of neural network parameters. The neural network is then used in multiple games in which it plays itself. If each of these games, for every move, Monte Carlo tree search is used to calculate the final outcome of each game, determines that game's value. The parameters are then improved by using a gradient descent or any of the more sophisticated accelerated descent methods. AlphaZero used stochastic gradient descent with momentum and learning rate annealing on the loss function for a random selection of states played. And that's it. Folks at DeepMind contributed a clean and stable learning algorithm that trains game-playing agents efficiently using only data from self-play. While the current zero algorithm only works for discrete games, it will be interesting whether it will be extended to more. And so this 3 years ago, and obviously it is now. And as you see, AlphaFold has been out today. So Church of Entropy, thanks for joining in the chat. So I mentioned to Jennifer these slides, and maybe we'll go over them again on Week in Review later. So let's look at some slides just to get some of the basics here of what's going on, and maybe on Week in Review. I guess if Jennifer wanted to pop on right now and help me go over these slides, you can. Otherwise, I'm going to go through some good slides I found to explain some of these concepts and some diagrams. I'm going to try to read a few papers. These are papers I'm going to get to, not today. These are more complicated multi-agent evaluation by evolution, more complicated machine learning techniques, and a comparison of machine learning techniques. Here's a most recent paper from AlphaZero related to chess, where they look at changing the rules of chess and what it does. Vladimir Kramnik went over it on chess.com. Not going to have time to go over that today. here is the white paper for Crazy Aria, which is a Crazy House version of deep learning. And I spoke with these guys on the internet once, and I'll probably go over their paper also at some point. This is going to be connecting it to neuroscience. So I have a lot of stuff on like what is a cognitive map, and the way that a brain might organize knowledge. I probably won't get to that today. Hopefully I'll be able to read this today. So did Jennifer, did you want to hop on and help me go through these slides? Or I'm going to enter full screen and try to give a little explanation of this. So let me just, I'll give Jennifer the link if she wants it. And I may not notice if she does come on, but okay, so let me just wait a second and then we'll go over these slides together and you get a good feel for machine learning. I did think I was going to read through maybe this paper, what does it mean to understand a neural network? And it goes over, kind of tic-tac-toe, which could be solved with just 3 rules to Go, which likely hundreds of thousands of rules or chess that the program developed in order to solve it. And what does it represent, like a brain signal? And so I had actually planned on reading this one today. And this one, Neuro-Inspired Artificial Intelligence, which this one's longer, so we'll see how much energy I have, which pretty good model for looking at the correspondence between the models of how thought works, so to say, from a machine learning perspective, computer perspective, versus a neurological model. And so this is a pretty good paper. And I have a lot more papers that, I'm not going to be able to read them all online, but so we'll see. I'm waiting for Jennifer to show up. So I can enter her, and then I'm going to put this into full screen. Okay, so let me just start. Let me start this bigger one. Deep learning tutorial. So this is from the University of Waterloo. Thank you for posting these. Electrical and computer engineering, robotics researcher from Korea. I'll put together some great slides. Deep learning researcher in Waterloo, Canada. Parkinson's disease project. So much props to you in your study. And so you've divided your slides. You got introduction to machine learning and deep learning, and then you have methods. Okay, so let me see if Jennifer's showing up. Okay, so Jennifer's here.
Hey, Doooovid, thanks for having me.
Okay, did you catch the beginning of the stream? Did you want to add anything? Or should
I just got here, but I did see that you were talking about entropy and neural nets. So I'm basically interested because I no kidding, I worked in this exact field for several years.
So I'll get your opinions on the stuff I said earlier later, and let me continue straight with these slide shares on deep learning machine learning tutorial. So here he has the Venn diagram where artificial intelligence is the main subject, of which machine learning is a subset of AI, and deep learning is a subset of machine learning, and neural networks are a subset of deep learning. Does that correspond with the way you see it?
Yes. because they're all technically artificial intelligence, that they're just implemented differently.
Yeah, so object recognition is a big field. Voice recognition that Jennifer has, speech recognition, and I have papers on this, medical devices, and so supervised learning is where you have training in order that the computer has a man-inputted label of what it wants the computer to recognize certain patterns as. That so when the computer says this pattern that you see equals this, and that's trained and implemented, and then you have a test as opposed to Alpha 0 that self-trains itself. And I guess it's somewhat formulaic. So I just found these slides, so I'm not exactly sure how he went through it, but so machine learning has a training process, a validation process, a testing process, and these come into nice curves. For image you have a concept of like overfitting, training error, and test error. So all these things are going to come up, and just want to get some of these terms. And honestly, these are just slides that I found, so I may not be able to make sense out of them. So let me just forward to. So deep learning. Learning methods which have deep architecture usually allows end-to-end learning, automatically learn intermediate representation, thus it can be regarded as a representation learning. It often contains stacked neural networks, thus deep learning usually indicates deep neural networks. But I guess neural networks indicates deep learning, but deep learning doesn't always indicate neural networks, but you're just further levels, and we're actually going to look at some of the mathematics. Eventually, these are all going to be explained in mathematical formula. So here's an example, possibly in the brain process. I'm going to read a paper of the pathway from the visual cortex that has multiple stages and intermediate representations of like a deep neural network where there's different functions being formed at different levels that have higher levels of applications, where the essential function could be formed at a simple level and deeper functions beyond the level that the way consciousness is likely to work, and even biological evidence does.
Can I just read from the wiki just real quick for deep learning? Just because I'm not sure what deep means, and I doubt the audience is either. It's just
go ahead, and I'll just.
It says the adjective deep in deep learning comes from the use of multiple layers in the network. So it looks like early work showed that a linear perceptron, which is what Aiken was talking about that one time, cannot be a universal classifier. And then the network with a non-polynomial activation function with one hidden layer of unbounded width can, on the other hand, so be. So it's when there's basically layers of computations. Thanks. That's all I want to say.
Yeah, and so that's what I'm mainly trying to do, is get definitions out here, because eventually these definitions and concepts are going to be reduced to symbolic forms and extracted from there. So you have neural networks, large parametric model like higher order polynomials, learn the parameters using gradient descent method, local minima problem overfitting, and so this is a mathematical concept that I've taken similar things. I'm not sure I ever used gradient descent method in any of my math classes, and we'll take a look at what gradient descent method is, but it's similar to methods that maybe like the Newton method or the Euler method, that but more complicated, maybe not even more complicated. I'm not sure if you used the gradient descent method.
It sounds like a reiteration of a calculus method. According to Wiki, it says it's the first order iterative optimization algorithm for finding a local minimum for a differentiable function. So it looks like a numerical method to approximate the first derivative being 0 and the second derivative being greater than 0, which is what a local minimum is.
Yeah, so the important part here that we're going to see related to alpha 0 is this forward pass and backward pass of the method. That the method uses a forward and backward pass, and the backward pass is actually called entropy. I mean, we'll see these formulas and why they're referred to as entropy and what information gets deciphered from going through these networks, and even how these networks are created, or if we could even understand how they're created. Maybe all we know is certain information that's given out through the forward and backward pass, and everything has to be calculated just from the values we're given from the forward and backward pass.
Well, I think understanding what entropy is on a theoretical level and that it relates directly to the number of microstates is super important for computers, because it looks like they're actually using microstate approximations to do some type of calculation. I can't tell what it is yet, but it's very interesting.
Yeah, this is going to be, precursor to the, the multiple truth hypothesis and greater things. And it's because AlphaFold came out in the news, and it solved a problem. It's 50 years old that people thought would possibly never have been solved, and it's this method that came about. And from a programming perspective, it's not that complicated. Like alpha 0 might have as little as like 100 lines of code, because it's really just mathematical formulas. Okay, so let's look at the methods that here he's got CNN, RNN, VAE, GAN. So what are those? What are they? So here's your popular methods of deep learning. You have supervised learning, unsupervised learning, and reinforcement learning. Supervised learning could be broken down into convolution neural network and recurrent neural network. Unsupervised learning could be broken down into variation autoencoder and generative adversarial network. And reinforcement learning includes deep Q network, actor critic, and policy gradient. And there's probably more than these, but these are just the most popular methods. And all of these methods have could be broken down into more and more methods. And as a chess player, it's interesting because if you play computers, the difference between many of the computers is what technique they use, and you could get a feel for the style of these techniques by the style of chess, so to say, that these different techniques produce, because they're all just statistical methods largely aimed at discovering, so to say, truth. Are you familiar with any of these methods, or just even supervised versus unsupervised, if we're talking about labeling? So here you have labels. So supervised learning versus unsupervised learning.
Sorry, I was muted, Doooovid. Yeah, I've definitely heard of these. Supervised learning is where there's interventions from the coder, and unsupervised is when there's just a bunch of data and the coder basically says to the computer, just do whatever you want with it. So it's asking the computer to find the patterns in it rather than imposing patterns by supervised learning. Sorry about that.
Yeah, so within unsupervised learning, the mostly generative model as opposed to discriminative model, you have here what is called explicit density and implicit density, which is the difference between variation autoencoder and generative adversarial network. And so we're going to look more into these, but these are important patterns, and even from a logical level of the different possibilities to go about looking for truth. So say, do you say all patterns have a similar assumption of probability being true, or do you pre-program in the probabilities of various things being true or not, and then to further break that down into these further parts, which will actually be variables in a mathematical expression, as we'll see shortly. So implicit density here seems to be trying to generate realistic samples. It's got more. So he's saying himself that he works mostly in supervised learning, static data like images. So Jennifer probably also would have the most experience in supervised learning, convolutional neural network, as opposed to sequence data as natural language, like recurrent neural network, which would be trying to make intelligence out of spoken speech, as I think like Jennifer and what she did, which was just voice recognition, would probably be convolution neural networks. I'm not sure if I'm right about that.
You are, because unsupervised learning doesn't use, it's unlabeled data basically, and our data that was used to train our model was all labeled. It was the NIST data where they get people to talk to each other on the phone and record that for a bit of money. So yeah, it's all supervised. I think the idea with unsupervised learning where you don't have labels on your data, the implication is that you are dealing with a deluge of data. Like you have so much data that you can't conceivably process it. So you're like plucking off metadata and trying to see something in that. That's my impression, but no, I didn't work directly with that.
Yeah, so here you have the convolutional versus the recurrent. So convolutional, fully connected layers, convolutional layers, where you have more important parts that have more data within the layer. That you might have a full layer, but within the layer, there's parts that contain more data than others, to form a network. And for image processing, the convolutional neural network is a layering method of the information to produce the important parts of an image or a sound, which could be at like a Fourier transform or a various mathematical or statistical method on the inside to conceptualize like what a Fourier transform does. Like I said, our ear is like a machine that performs Fourier transform. It's like, no, it's a device that allows us to hear, but there's mathematical explanation to what's going on. So here you have a convolutional block, and it's called the pooling layer, activation layer, and the convolutional layer. And it could be fully connected layer, convolutional layer. Is this familiar to you?
Sure. Just for those of you who don't know, convolution involves, it's a fancy way of saying putting two things together.
So here you might have a complicated convolutional architecture of a breakdown of some neural net representation of data. And like we saw in the previous one, each point on this neural net could have useful information in terms of forward propagation, backwards propagation, number of times the node has been gone down, and possibly some sort of representational result of the outcome of what happened each time in the past it went down that node. And from a chunking level of neuroscience, we're going to say it's possibly also that that operates on a similar principle. So here, application.
It looks like what's special about convolutional neural nets is that they are shift invariant or space invariant. So that means if you like double the size of a picture, you get the same score as if you hadn't. So that's convolutional neural networks specifically. So it looks like it's pretty much just for images, video maybe.
Yeah, so as opposed to recurrent, where you're talking about the same actor that's going to be appearing again and again and making more sense of it. That could be, like actual person identification, or making sense of language, sequenced data, not static data, but sequenced data. And you can see the network is different. The amount, so here you have a recurrent network, and the actual, now we're going to get into some complicated equations. So I'm glad Jennifer's here. And the papers I'm going to read eventually using the multiple truth hypothesis, likely the whole thing will be able to be reduced to a single equation. And do you have any comment on these equations here?
Not quite. It's a bit tough for me to see them.
Yeah, they're not really defining the term. So I have other stuff where it defines this. So if you're looking at a transistor, just a logical method, or some sort of heuristical algorithmic method of short-term and long-term memory that may follow combinations of neural information and introspective. So applications, you see, you could have one-to-one, one-to-many, many-to-one, many-to-many. There's different forms of many-to-many that would require recurrent networks, and speech recognition, because not just like voice recognition, maybe to some level, but speech recognition, where it's these recurrent words or themes that the computer could recognize in order to interpret speech or even put speech together.
Cool.
So here are even more possibilities: algebraic geometry, machine translation with attention mechanism. It's possible even to include a concept of attention within that. Okay, so now you have unsupervised learning. And within that, we had variational autoencoder and generative adversarial network. And there's explicit or implicit density. And it could be task-specific features, like looking at these pictures and you want to identify the person and estimate the emotion. So two different tasks of using this, the same data to recognize a person and recognize an emotion, presumably something that our brain, does, the human brain does, and there's a lot of research on that also. So labeled data is difficult to collect. So you could have labeled data in a way that you have data that it's been looked at, and after it's been looked at, it's given a label. And that's, from that label, in the future, you could determine what to do with that label. And, attempt to learn a good representation. How do you know what's good or bad? Which one is good or bad? Is it better organized or unorganized? And that's possibly a subjective question.
Looks like their solution is to turn unsupervised learning into supervised learning. Because I guess at some stage, no matter how good your code is, you've got to intervene at some point just to do. I believe my colleague called it a sanity check. This is like the main guy at MIT who works in this domain of speaker recognition. He's like, remember, Jen, you want to do a sanity check. I always remembered that. But I just wanted to say real quick, like with recognizing the facial expression, that image that you had with all the different facial expressions of that woman. So the way the computer sees that problem is that if it's a actively trained one, you give it a bunch of labeled data. So a bunch of people making the exact same face. You train it to recognize that face, and then you give it new data, and it'll test using its extracted features that were common to that face amongst many images to see whether it finds them. So that's why these things can be quite accurate. And they can contain it. They're really just limited to the amount of training data that they have. If the architecture is good, go ahead.
Yeah, and or self-generation of training data, if that's possible. And we'll see.
It might be with something like, I think it's called Simulink. Do you know that program? It's like a MATLAB adjacent program. I think it's called Simulink. Correct me if I'm wrong, but it basically does simulations.
Well, there's many. I mean, the chess examples.
Yeah, so you could generate data using a simulation and then train your model with simulated data, but then it would be the bottleneck of accuracy would then come down to how accurate is your simulation. So there's even more problems inherent to that. So just for the applications, it would be even more nebulous to do it that way.
Yeah, and basically these are all, so here you have, so you have autoencoder, variational autoencoder, and the idea is to minimize reconstruction error, that you get some sort of image and it has to be encoded and decoded like sound in your computer, that I'm talking to a microphone and it's transferred into a signal that's being sent through satellite or fiber optics or however people are receiving their internet, and then at the other end being converted back into a sound wave, and that's how you're able to hear me and Jennifer right now. But reconstruction, there's going to be an error that because it's usually the size is minimized, and there's a reconstructional error. So variation autoencoder, minimize reconstruction error and regularization loss. And we'll see what regularization loss is, and the various mathematical techniques like a Gaussian and Bernoulli, and the various mathematical techniques that maybe Jennifer is familiar with from other areas.
Yeah, you just think about it in general. Okay, remember that image with the lady? Now that I think about it, I think actually we might have funded this research. I think my unit funded research at University of Waterloo to come up with a really good compression algorithm for images. And they did a good job, I think, by doping it with higher frequencies.
That's probably why this guy produced such good slides, because I was just looking for some good slides, and this guy had relatively from the better slides I found.
Yeah, I think he's worked in this domain for a while. But basically, if you want to understand what they're doing, to imagine that image broken down into a bunch of frequencies, do a Fourier transform on those frequencies, remove some of the coefficients, and then you got your compressed waveform. To regenerate the image, you just have to do the inverse Fourier transform on the compressed data, which gives you an image that's similar but not equal to the original.
Yeah, so we're going to look at some of the exact mathematical techniques, but you kind of understand it's a statistical method, and there's you're going to do your best with the minimum energy possible, and it come out in different ways. And there's a lot to cover, and we're going to get more into it. And I didn't, me and Jennifer didn't really study or prepare that much for it. But so let's look at the GAN, the generative models, which here might have more concepts included, like maximum likelihood, tractability, Markov chains. So I mean, it's appearing that GAN is a superior method just from what it's looking at, although I don't see a clear explanation here in these slides that maybe there's not of so is anything left useful in this? Here's a statistical, the Bayesian process that we've talked about, which is basically a simple equation of combining the probability of two separate events into one of two separate events that have their own probability into one, distributing the probability factors. In a Gaussian approach, which says not scalable, maybe look more into it. That Bayesian becomes the most popular method for most of these.
Do you know why Gaussian doesn't scale?
No, I don't. Not offhand.
Because as intelligent as we are, we actually really suck at implementing the Gaussian elimination algorithm into a computer. You're familiar with this algorithm that has 3 steps, right? Interchanging 2 rows, adding a multiple of a row to another row, etc., multiplying a row by a number. That's the Gaussian algorithm. We have a hard time getting the computer to see that the same way that we do. So to scale Gaussian approaches would require scaling of that process, which would exponentially increase the computing power required, which would defeat the purpose.
Awesome. So anyone wants to look at those slides, I think I put them at the beginning, and I found another set. These slides were more mathematical, but more straightforward. So I did the first one, had more pictures. So here you got Dongmin Lee, maximum entropy reinforcement learning, stochastic control. This is the outline. We can talk about reinforcement learning, Markov decision processes, Bellman equation, exploration methods, maximum entropy reinforcement learning, and from soft policy iteration to soft actor critic. Are you familiar with any of this stuff?
Well, I actually had the idea to use maximum entropy of, I had an idea to use entropy to approach these calculations like maybe 10 years ago. So I'm glad to see that they're using entropy somehow, but no, I'm not familiar with this particular implementation.
Okay, we'll see. And this one's pretty mathematical. So intelligent systems imply that data plus intelligence becomes information. And information plus intelligence becomes decision. And this is very related to like free will and all these chess studies. And the hard problem of consciousness is, is this actually what's happening, and even representative of this? But you're implying that there's extrapolation from data to information and extrapolation from information to decision. And that could be programmed into the computer. I'm saying factually, that's how all these, devices and that are taking over, AI are working. And, so it's a reward, stimulus, agent does an action to the environment, and the environment causes a reward or punishment back to the agent based on that action. This is basically the principle of karma, right? I mean, reinforcement learning is basically parallel. That's why, God forbid, Indians dominate IT and computer programming, because the Vedic thought system is so similar to the current database structures used in AI. And
I think the link is that Vedic maths is all algorithm based, not algebra based, and computers is all algorithms.
Yeah, so this is a basic karmatic action reaction feedback. So reinforcement learning provides a formalism for behavior, the problem of a goal-directed agent interacting with an uncertain environment. An interaction leading to adaptation by feedback and decision. So distinct features of reinforcement learning: there's no supervisor.
Yeah, also having a bit of trouble seeing. It is a bit small. I don't know if you can I doubt you can make it any bigger. I just wanted to let you know.
Yeah, this is the best I could do. I put it in the chat so you could open it yourself on slide 6, but I'm reading the important information, and the diagram is more important than the words because I'm reading these words. So they said there are 4 distinct features of reinforcement learning. There's no supervisor, only a reward signal. Feedback is delayed, not instantaneous. Time really matters, whether it's sequential, non-sequential, a trade-off between exploration and exploitation. And reality, this is all like rules of karma, but we'll talk about that later in week in review. Let's keep it to
this comes to a really important point. It's the concept of a conservation law as applied to a computer. So if you look at number 4, it says there's a trade-off. So the computer can either be exploring or exploiting. So it can't do both at the same rate at the same time. So I just wanted to bring that in. There was a question in the chat. Reward implies a value, judgment, or call. How then is value determined? Did you want to field that one?
Well, we're going to get to that in mathematically, and we'll talk more about that in week in review. of how value is determined. But yeah, but that's an important thing to consider. And the purpose of this is to determine a value, and so that's what we're gonna get to. And it's possible you could have the systems where there's a mixed value of exploration and exploitation. So reinforcement learning is, and then you have deep reinforcement learning. So reinforcement learning is sequential decision making interacting with environments, where you have the what we had just discussed of reinforcement learning, that there's sequential decision making interacting with environments. Deep learning is the representation of policies and value functions. So this is really the answer to the question he asks is on this slide. So there's a process of reinforcement learning, which is basically like trial and error. You could consider it almost like even like a Turing machine, simplicity, where you interact with the environment and you get some sort of stimulus back of how that interaction went, and through trial and error, you come up with patterns of a better way to interact with the environment based on the reward and punishment stimulus. And so deep learning is a representation of policies and value functions. And that's basically the question that you just asked, is there's a policy that through trial and error or deep reinforcement learning, that I've devised a rule of how to interact with the environment because it works better, like a chess player. So this is really common in chess, and that's why I'm going to be talking so much about chess, because like any chess player, would easily understand what I'm talking about. And then a value function is that how do you evaluate that policy? That how well does this rule that you came up with actually work?
Yeah, we have a really hard time with self-driving cars because we can do like the lower part of the decision tree, because ultimately computers is not a quantum computer, it's a decision tree. So it's like yes or no, boop, yes or no, boop, yes or no. So we always have trouble with what they call the chaotic systems, because our decision-making process is quantum. We can do it super fast. We can recognize like, oh no, there's a dog on the road, I better slam my foot on the brakes. Whereas the computer has no capacity for information centralization that way. So it's just going through a series of like yes or no gates, being like, oh, do I need to stop the car? No, yes. What am I recognizing here? Oh, and then it's usually that lag time when it's trying to figure out what it's recognizing where the problems happen.
Okay, so let's just say out here the challenges of deep reinforcement learning could be huge number of samples, not even millions. If you're talking about solving visual like self-driving cars or something, it's going to be trillions, near infinite. I mean, it won't be near infinite, but it's going to be much higher than millions. Fast, stable, hyperparameter tuning, exploration, sparse reward signals, safety, reliability, simulator. So these self-walking machines or robotics. So back to the central diagram in some more basic terms. So you have the state of the environment system, that whatever is happening is occurring within a larger state, saying that there's me or Jennifer, but we exist within, like our dwelling, our family unit, our city, our country, the world. So there's an environment, and then the system that there's already rules that are dictating how the environment that we're in is acting. There's an action determined by the agent that affects the state. That there's a like free will type. Why free will is such a common way of understanding it is saying that there's a separate agent that performs an action on the state, and then the state, in reciprocation to that action, evaluates the benefit of the state of the action. So it could be from like like the difficult question of spirituality is in free will is how do you, is there such a thing as a separate agent, and the precursors and assumptions. But so here you have the assumption that there's a separate agent and a separate action on the environment, and then the environment is going to return a reward or punishment. And maybe in Week in Review we'll talk about the other possibilities that could go into a karmatic model. And here is, we're going to start getting into the mathematical logical representation, where state is defined as S sub t, in of a set of the larger S state to action A sub t. And policy is a mapping from state to action, and here they're defining it as pi, where pi is the policy, and the policy is a mapping from state to action, and that's either deterministic. In that case, pi of the state equals the action, or it's stochastic randomized, and then it's a probability where it's not a simple one-to-one correlation between the state and the action, where it's a randomized probabilistic model. Do you want to comment anything before I go further?
No, go ahead.
Okay, so policy is what we want to optimize, and the goal of reinforcement learning, that there's an agent who has the ability to act on the environment, and that environment will return a reward or punishment based on how we act. And within that, we want to devise a policy of how we act within the environment. And from a machine learning that could be statistically done, like I mentioned in AlphaZero through Monte Carlo, and just doing like a rollout or the maximum trial and error that's available in the allotted time. So this is also, are you familiar with Markov decision processes?
Yeah, I've heard of it. I'm not familiar with all the ins and outs, though, so it'll be good to go over it.
Yeah, I mean, this is just a brief, as I said, like multiple truth hypothesis is going to call upon the best of all current statistical methods. And I never really worked with any of these statistical methods. I'm pretty educated. I've taken courses. I've even passed courses on edX on this stuff. But these are very important to logic and statistics, and almost any field that uses statistical methods will come up. I'm probably most familiar with it through chess programs, but this used in, so a Markov decision process is a tuple consisting of S, a set of states, a set of actions, a state transition probability, a reward function, and a discount factor.
So in the case of chess, the states would be the board, right? And that would include all the information about the different types of players on the board. And then the actions are the way that the players can move, right? Like how pawn can go 1 or 2 forward, etc. And then the probability would have to do with like your chances of winning.
We'll see that may not be. I'm saying that it could be the state includes all the rules, and the actions are the possible actions based on the rules. There's not a division that all rules fall into states, or could there be rules within actions? So like whether the pawns move 1 or 2 or the various things, those are all within states, and actions is just all of the various possibilities within the rules.
Well, you could look at the set of states as the set of all possible configurations on the chessboard, but there's no way that's what they're doing, because not all configurations are independent, or would they ever happen, right? So it's going to be some reduced set of the space of total chess moves. No, I mean chessboard configurations, because like you say, the information's got to be included there somehow.
Well, I was saying the state is the current position and all the rules. The action and possibly the history of how we got to there. The action is, given the current state, the various possibilities that can be done at the current time. So action doesn't include any rules. The action is just the possibilities at that given time, and all other information is contained in state. So Markov decision process just has 5 pieces of information: the states, the action, the state transition probability, a reward function, and a discount factor. So you could put that probably into summation or an integral form to find an optimal policy that maximizes the expected cumulative reward in this Markov process. If you, the symbols, so this you see how it comes in function where t becomes a variable that's common to all the other denominals, like over time. In a value function, the state value function of a policy is the expected return starting from a state S under executing pi. So pi is a series of actions, not necessarily just one action.
It's a product, isn't it? It's like the sigma, but for a product.
Pi is the policy that is
never mind.
used
They
to devise
it.
the best action determined on the state. So you're saying, given the various state, what is the best action to take? So pi is a policy that helps you determine the best action to take given the current state. Right?
Yeah, it makes total sense. I think the chess example is a bit complicated. I'm just looking at the chat. It seems people are a bit confused, but would you know how this would apply to chess?
Yeah, maybe I'll keep the chess separate or do it separately. And I have papers that are specifically dedicated to chess, and you'll see how these functions come out in chess. And in reality is that chess programs work exactly according to these equations. But let's finish this slideshow, and that's going to be too complicated for today, and I'm not even an expert in that. So the Q function, the action value function of a policy is this respected return starting from state S, taking action A, and then following policy pi, leaving your grand formula on the bottom, Q of pi, which is in a truth value function is saying, given this action and this strategy, what is the likely outcome starting in this state?
Just to be clear, it's not Q of pi, it's Q pi of S and A.
Yeah, thank you.
Sorry. I just want to make sure we have the lingo correct, so when we go to write our books that everything's good to go.
Yeah, I appreciate it. My mom's not going to be able to help me out with that part. Okay, so to find an optimal policy that maximizes the expected cumulative reward, therefore we have an optimal value function. The optimal value function is the maximum value function over all policies. So when I talk about the multiple truth hypothesis, it's similar to this equation. The multiple truth hypothesis will very likely have a similar, this is in the Markov decision processes form. There's other ways of looking at besides Markov decision processes. But when you're looking at the optimal value function, the optimal Q function is the maximum Q function over all policies. So I talk about the set of all possible axioms. So you're saying here you have a state, and you might have an infinite amount of policies, you might have an infinite amount of actions. And the optimal value function, given the infinite possible actions, the infinite possible policies, still, you could estimate using statistical methods an optimal value function. So this is the precursor to what will be the equations to the multiple truth hypothesis that could be applied to all truths, period.
Great. It's so exciting and interesting to see this model get developed.
Yeah, so let's look at the Bellman equation, because it gets more complicated. Just showing how, something like this, the MD, this top one could be similar to the MTH that might be able to reduce to such a type statement that is expandable. So the Bellman equation, expectation equation for the value function. And the value function is going to help you determine the best possible policy from all policies. So the value function is the unique solution to the following Bellman equation. So this is beyond so if you don't have any comment, I'll just scroll through these, but you're just saying in the future, this will be similar to what the multiple truth hypothesis is going to look like. I don't know if you have any knowledge of Bellman or you want to comment on this.
I know it's going a bit too fast. It's okay. It's just a bunch of math. I think mathematically, it's more important that we sort of understand the algebra than all the particular formulas, so that we can express our own ideas mathematically and ultimately generate our own formulas that nobody will be able to read.
Well, no, I mean, these are equations that in theory you could plug in the values and get a prediction to be valuable, and even program that you don't see these equations when you play chess against the computer. You just play against the computer. So if there was like a computer program, multiple truth hypothesis, a person would enter in their axioms, and the MTH computer program would do all the plug and chug and give you a value.
Very interesting.
So you have policy iteration, value iteration, temporal difference learning, Q learning, and these are represented in mathematical terminology what policy iteration is, or a method that you're looking like. So now, like in a chess program, that like under a Markov system, find the best policy, which is kind of like saying find the best move, but not the best policies. Action, find the best move is find the best action. So when you program a computer, a chess computer has been programmed, the policy is programmed into the computer to help it find the best action. Under artificial intelligence, the policy is figured out by the computer by itself, sometimes supervised, sometimes unsupervised, as we saw in the other slides. Does that make sense to what we're saying, that the possibility of these functions in unsupervised, supervised, and what was the other? I already forgot the slides. The other.
I'm not too sure, but this actually does relate to chess, because what the computer is seeing is a particular configuration on the board, and then it's saying, given this configuration and given this set of all possible trajectories of playing that begin at this location, which one converges to me winning the fastest and by what series of moves? And it recalculates that each time that its opponent plays.
Yeah, so I'm going to skip over these methods and let's get to the maximum entropy reinforcement learning. So what does entropy relate to information? And I don't think we covered this yet. I mentioned it a few times, and maybe we popped it up on Week in Review.
I think we looked at Boltzmann's relation. So for those of you who remember, who watch Week in Review, we've got S, which is entropy, equals K ln the number of microstates, which is usually denoted with a W or an omega, which is the W in Greek letters. So this is a different way of looking at it. This H of P equals some Pi log P, but we can see it's the same generic formula for entropy. You have a number times the log of another number. So this is the generalized entropy formula, whereas the Boltzmann equation is specific to an ideal gas, I believe. Go ahead.
Yeah, and so this is going to be the related to the loss function and information theory. So information theory and reinforcement machine learning has the same problem, and we call it a problem, but entropy relates exactly in the same way to information theory. And we'll see how the equations work. And so here we're already looking for a high entropy policy. So entropy affects information. And so we're looking at the
important thing to remember is that high entropy equals low energy, and we generally do want low energy solutions, right? Because if we can solve a problem using high energy versus we can solve the same problem using low energy, makes more sense to use less energy, like for cheapness, So that's where the maximization of entropy plays in.
Yeah, so the part I skipped, saying the exploration, that we have an unknown we want to explore, and can we algorithmically solve the issue of exploration versus exploitation? And so maybe that's important. You have the 5 different methods here: the greedy, optimism in the face of uncertainty, Thompson sampling, noisy networks, information theoretic.
I guess we got to add Super Librix's incredibly brilliant method to that too, right? Badoomts.
Yeah, so greedy, the idea, choose a greedy action, choose a random action with a probability, it's simple light computation. I'm gonna have to look more into these methods, but as you search for information, the entropy is going to be a problem. But as you're exploring a new region, you're going to face up entropy, and it could be put into a policy because you know the law of entropy, that you could calculate the effect that entropy is going to have upon your value search for the right policy. So what's the benefit of high entropy policy? So here's the entropy of policy, and there's a higher disorder in policy pi. So you're saying riskier behavior.
It sounds like they're trying to increase the scope of predictions that the model can make by maximizing the entropy of the phase space. So basically like fanning out the total volume of possible outcomes by maximizing entropy. It almost seems like they're trying to encompass new risky, more extreme behaviors into their model, perhaps.
Yeah, so the difference between the standard machine deep learning problem versus maximum entropy in terms of the Markov, and you see that the maximum entropy adds in a maximum entropy factor. And that could be related to the Bellman equations that in here that he even goes through proving the Bellman equations. And you'll see the relation to machine learning. Like I said, the backwards and forward propagation, where each discrete node or point, you're going to have certain values that are given to you that form your neural network or your policy. And
speaking of computer karma, looks like we've managed to assimilate the concept of greed into a computer. It said something there about greedily increasing the entropy. It's kind of funny.
Well, a policy or strategy that a computer might take that we assign a word greed to. So it's just a method or strategy that mathematically could be employed, and you just give it a name greed because it might correspond to the psychology of the. So what's the advantage of maximum entropy? No maximization involved for computation. Exploration, high entropy policy, structural similarity. You can combine it with many reinforcement learning methods for standard machine deep. And your soft policy iteration to soft actor critic. So these are pretty complicated. If you've never heard of this stuff, I might have to skip it, but eventually, I'll read the definition. Soft actor critic, model-free version of soft policy iteration, soft actor critic. Soft policy iteration, maximum entropy variant of policy iteration. Soft actor critic, maximum entropy variant of actor critic. Does it make any sense to you?
Not quite.
Yeah, I have to look. I mean, these were just slides to explain it, and you'll see that entropy will be a major theme, even in machine learning. That the main factor that prevents the computer from, so to say, solving and producing better factors is entropy.
I think they're actually finding the entropy of a system and then using its maximum state to predict the most likely outcome is more what it sounds like.
Yeah, I guess because entropy is just a factual factor that you have to deal with, but dealing with that factor, you could maximize the equations.
The power of entropy is that it's a single number that transcends the entire system because it's based on the microstates, right? So no matter how many different terms you need to add up together to get your final entropy term, it's just one number. So that's computationally extremely valuable because it shortens up these complicated sort of convolutional nets that the data has to go all through.
Yeah, so pretty interesting. I think I think I'm going to try to read 2 papers to further, just get these terms and definitions out there, this current state of the model. And then, I'm not sure if this man who was in the chat earlier who contacted me for his book is going to come on Week in Review later. This guy, some man, Charles Moskowitz, he written a book on pathology, but I think he's just going to appear in the chat. I don't think he streams. So is there anything else you want to add or on the topic of AlphaFold, AI, neural networks, neuroscience, relation to multiple truth hypotheses?
I still have to do a bit more research on the new development of the folding. I've heard about it from several people. They're curious to know how it works. So I'm going to look into that and explain.
I covered it in the beginning of this video if you weren't there.
Oh, awesome. I'll check it out.
I haven't read the paper from parts of the paper. But it's just a simple concept that that proteins, they have a simple peptide structure like a long line, but they fold in upon each other and attach at certain points. And by the time these large proteins have folded so many times on each other, it's a very complicated structure that was beyond the ability to predict. That there was always thought that predicting the structure that a protein would take is beyond computational possibility, and they assigned the problem to this unsupervised machine learning algorithm that back and forward propagation, the methods that explain, and why I went through these slides to explain the method that it did, and it was able with close to 90% accuracy to predict these structures that before no one was ever even more than 30% accurate.
Very interesting. Looking forward to delving into that.
So for the multiple truth hypothesis, it's very significant because winning at chess is not the same thing as predicting material outcomes in the material realm. So from that realm, like Doooovid likes chess. Chess is probably actually more interesting than protein structures, and more people care about chess than they do about protein structures. But from an objective, understanding the power of these computer algorithms that may have largely been developed related to chess, because chess is the the father of all board games, are now proving to be substantially useful in all fields. And Doooovid even claiming that at some point soon, they're going to put Alpha 0 that's just going to solve all the answers to all the problems in the universe.
Awesome. Well, thanks for having me. And it'll be interesting to go over these subjects in more detail and see the difference between Boolean determinism of chess and the quantum determinism of these folded proteins.
Okay, awesome. So I'm going to read 2 more papers. So I'll see. What time do you want? 7 o'clock?
Sure. We'll start Week in Review at 7 o'clock. Hope to see you all there. Looking forward to it. And thanks for hosting the stream, Doooovid.
Okay, yeah, thanks for coming on and helping explain some of these mathematical concepts. And these are very complicated. The most advanced algorithms in AI. Jennifer has quite a bit of background in mathematics, but I wasn't expecting her to be familiar with these equations on site. But her knowledge of math and these equations generally better than mine, so I appreciate her help. So I'm going to read 2 more papers. And I see the monthly Horde tournaments going on. I might play a few more games of chess, the Horde, but there's 3.5 hours, so I'll probably play a few games. I don't think it's worth streaming much. Here we go, message. Okay, so I want to read 2 different papers, and I'm going to read this paper from DeepMind. This paper is published from the research at DeepMind, and then another paper from DeepMind related to various topics. So just check if the sound's working. Jennifer looks like she got off, so I'll take my earpiece out. Okay, no chanting today, Rune. We'll chant later tonight. I'll keep it intellectual, and hopefully these streams will be useful in the later for people who want to learn more about these subjects or want to understand the multiple truth hypothesis. Okay, so what does it mean to understand a neural network? Lily Crapp and Courting, July 2019. We can define a neural network that can learn to recognize objects in less than 100 lines of code. However, after training, it is characterized by millions of weights that contain the knowledge about many object types across visual scenes. Such networks are thus dramatically easier to understand in terms of the code that makes them than the resulting properties such as tuning or connections. In analogy, we conjecture that rules for development and learning in brains may be far easier to understand than their resulting properties. The analogy suggests that neuroscience would benefit from a focus on learning and development. When we build networks to solve image recognition at human-like performance or are strong at playing the game of Go, we ended up using a few computer screens worth of high-level computer code. We undeniably understand these lines of code, and we teach how these systems work to students in our deep learning courses who also obtain a meaningful understanding. After training, we have the full set of weights and elementary operations. We can also compute and inspect any aspect of the representations formed in the trained networks. In this sense, we can have a complete description of the network and its computations, and yet neither we nor anyone we know feels that they grasp how processing in these networks truly works. Said another way, besides gesturing to a network's weights and elementary operations, we cannot say how it classifies an image as a cat or a dog, or how it chooses one Go move or another. For neural networks, there's no doubt that the understanding that we have currently about their properties after learning it is massively more shallow than the understanding that we have about the code used to train it, the rules for its development and learning. One day we may develop a way of compactly describing how neural networks work after training. There may be an intermediate language in which we could meaningfully describe how these systems work. A useful intermediate language would allow us to write high-level computer code to directly construct powerful neural networks for image recognition or playing Go without resorting to iterative construction of the network via learning procedure. However, we cannot currently offer such an intermediate description for artificial networks, which we have arbitrarily better access than to brains. As such, even if meaningful descriptions exist, for the moment, we best understand neural networks in terms of their mechanisms for development and learning. Okay, so here you see the notion of compressibility and an A. Unbeatable performance at tic-tac-toe can be obtained with just 3 rules. These rules can be ordered by their importance. Unbeatable performance at the game Go needs many rules, so many in fact that we cannot know that number. Importantly, the rules are heavily tailed. If we have any small number of rules, the remaining rules will generally still carry a lot of information about how to further improve on the task. Humans have long tried to distill the game Go into instructional books and have to a large extent been unsuccessful at doing so. The question of where on the axis the brain is situated, the brain might be easier than Go to compactly describe, or the brain may be much harder than Go, affording no compact description under any realistic assumption. In this paper, we will discuss issues of complexity as applies to neural networks and other artificial systems. These systems are fully observed. We have a total description of all the involved functions, and nonetheless, we have trouble producing a meaningful understanding. We will use the consideration as a backdrop to ask what we mean when we talk about understanding neural computation. We will argue that the brain's generative process is not that unlike that of neural networks, since it obtains information from the world which it stores as a distributed pattern of weight changes, a pattern that is remarkably hard to wrap one's head around. We will conclude by suggesting that, at least for the moment, neuroscience should focus on understanding development and learning. And an artificial system that is as good as humans at a broad range of tasks be compactly expressed. The learning rules in artificial systems are compactly expressed in the sense that they can be written in a few pages of high-level code. And at least To us practitioners of machine learning, it feels like having such a compact description is necessary for meaningful understanding. Having such a compact description offers us leverage. We can produce variants of the same kind of ideas and use them to solve a broad range of useful and interesting machine learning problems. Maybe humans or other intelligent beings can figure out ways of meaningfully arguing about non-compact systems, but at least so far, compactness is necessary for what we would call a meaningful understanding. Central to our arguments is the idea of compressibility. We have introduced it with a simple scenario, the game of tic-tac-toe. Well, there are 255,168 potential games. We have a policy of just 3 rules that allow unbeatable tic-tac-toe performance. In the game of Go, in which computers have recently started beating world champions, there's no known compact way of expressing the instantaneous valuation of a position. This is at least in part due to the fact that there can be exponentially many games of Go, although the set of reasonable probable games is probably much lower. In such a domain, knowledge that lowers the number of allowable games by a factor of 2 will be essentially useless. Neural networks that capture effective policies and value functions for Go reflect the complexity of the game. Systems that solve a broad range of interesting problems at human levels should be less compressible than specialized systems that play Go, or neural networks that recognize visual categories. After all, humans can do both. In complex domains, approximate systems that are more compressed tend to have poor performance and so do not truly represent a way of avoiding the problem. We may thus expect broadly applicable intelligent systems to be hard to compress into a small size. Computer scientists have worked extensively on the problem of compressing larger neural networks into simpler and more describable systems. With the rise of popularity of distillation techniques and a renewed interest in the field of computational complexity, we started to understand more about compressibility. For distillation techniques, we know that networks trained on ImageNet, a popular 2012 machine learning benchmark that required the classification of natural images, cannot readily be compressed to fewer than about 100,000 free parameters. We want to emphasize that these compressions, even of the ImageNet case, are not in any meaningful sense human understandable. Even the famous and somewhat trivial networks that solve the MNIST character recognition problem cannot readily be compressed into a format that humans find readable. Moreover, human performance includes knowledge of roughly 30,000 categories or objects, and arguably they on average know a lot of information about each of them, possibly megabytes thereof, and certainly more than a few bytes. Humans also appear to know more than a megabyte worth of information about their own language. Human-like performance seems exceptionally hard to compress into a compact representation. How are neural network scientists trying to understand their networks? The primary look for a phenomenon relevant for optimization, such as vanishing, exploding gradients or exploding global dynamics during the process of generation of system. Perhaps most common in practice is looking at histograms or the unit activization of and derivatives to see whether learning is halted or being slowed for a trivial reason, offering clues as to how to adjust learning rates or other hyperparameters. However, such analyses are used almost exclusively to diagnose problems in the engineering process that arise during the construction of the system. They do not provide a path to meaningful understanding of the computations done by the systems they build. Ongoing work in deep learning fields aim more intuitive understandings of the computations in neural networks. Scientists study the sensibility of outputs to changes in the system to ask what matters. They ask which stimuli can fool a system. They visualize elements of a network. They analyze what happens if a system is perturbed by removing units. However, no one who is familiar with these approaches would say they offer a good understanding of models like AlexNet, AlphaGo, GPT-2. These approaches remain far from offering practitioners enough understanding to be useful to improve networks for task performance. Returning to the question of compressibility, we may ask why we should expect neural networks that exhibit human-like performance to be hard to compress. The world in which humans live is undeniably complicated. Much of our world is built on peculiarities which are obviously incompressible. Like, let us choose balloons as an example. Adult humans know a lot about balloons. For example, they're made of rubber or aluminum foil, often held by kids or clowns or read in famous songs. And yet, it seems unlikely that we're born with knowledge of balloons. We have similar incompressible knowledge about any of the many categories of objects people know about. Estimates of how much humans know vary widely, but suggest that compressibility is limited. The important result is that the bulk of information we need to specify A working model comes from the world, which is complicated and arguably not compressible. There are domains where the world is simple, and then we should be good at building models. And there are domains where the world is truly complicated and is presumably hopeless to communicate a working model of such behaviors. Given just the architecture and weights of an already functioning system is not very useful, except with respect to the exact task that it already solves. Knowing the learning rules, architectures, and loss functions used to train systems are far more useful for future alterations and interventions one might want to make. It's an analogy to neuroscience. Humans are not neural networks, and yet the brain has ubiquitous plasticity. Specifically, we know that plasticity allows change in the brain to enable good performance across new tasks. As such, it is hard to see how the arguments we made above about artificial neural networks would not carry over to the human brain. To the level that insight holds, this may suggest that understanding representations which may be viewed like an artificial neural network after training may be outstandingly hard. We concluded above that for artificial neural networks, the focus on objectives, learning rules, and architecture is most promising. We do not see why the same argument does not carry over to neuroscience. It may currently be prohibitively hard to understand connections, strengths, and representations, even if architecture's learning and development can be meaningfully characterized and communicated. So where to now? However, while we may not be very hopeful about communicating a working model of the dynamics, we can still hope to communicate how biology, nature, sets up in the brain. After all, the complexity from DNA is upper limited by 6 times 10 to the 9th bits of DNA, and that information is hugely redundant, largely non-coding, and only affects change through some 20,000 genes, most of which undoubtedly do not code information for brains. That being said, we cannot know the amount of information collectively communicated by non-coding parts of the DNA. With the increased availability of genetic tools, we might be able to get closer to such principles. The basic biochemistry of cells is somewhat bounded in complexity. There are also so many types of neurotransmitters of channels that appear relevant. The development process setting up our anatomy as well as cell types promises to produce the backbone of our learning. We hope that we can understand them. Well, learned information is unlikely to be compressible. We may at least hope that biological information is learning rules and anatomy. The breakdown into parameters, nurture and principles, nature is precisely the breakdown that AlphaGo and AlexNet papers use in practice. They offer pointers to tasks and related data sources from which the vast majority of the incompressible and non-communicable parameters will be extracted, and then document the architectures, loss functions, learning rule, and optimizations approaches used. The last 4 pieces are easily expressed in small human understandable equations and formal recipes. We cannot communicate the data sources in any straightforward sense. While we could read the contents of the images and their labels to another person, they will not meaningfully understand their totality. And yet, we do understand the generation of neural networks. Not only do these recipes offer replicable means of producing workable systems, they also offer the kind of understanding that affords ways of pursuing useful and interesting interventions and predictions. There's a widespread belief that neuroscience, there can be a meaningfully mid-level model of the dynamics of the brain that both can be communicated and work for complex tasks. The idea is an analogy to physics and quantum mechanics. The state of a gas cannot meaningfully be communicated since every gas atom may exist in a high-dimensional space and there are many atoms, but in statistical physics, the state of the gas may be compactly described in terms of a few variables like temperature and pressure. And these mid-level descriptions can afford high accuracy predictions and control. From this analogy, it's sometimes argued that compact mid-level description should exist for neuroscience. Indeed, a lousy model of how eye movement is computed in human might enable us to better predict movements for some practical purpose. Such mid-level descriptions of the computations carried out by the brain may thus be interesting. However, the more complicated problems we discuss in this paper, the analogy quickly breaks down. In the gas case, all atoms are the same, are exchangeable, and have short memory, while in brains, each cell may be unique and have a memory that effectively goes back to the birth of the animal. Moreover, the argument we made here suggests that such a compact mid-level model of computation cannot have the property of actually working in the domains of brain performance, where the environment cannot be compactly communicated. Thus, the analogy to physics may be misleading in the context of neuroscience. So, some diagrams. Dividing theories of brain function into principles and data. If the brain is not compressible, we can at best divide our description of it into a set of complex principles instead of non-compressible data. We may then hope that the way the brain converts the data into computation may be understandable. They're saying the data in the brain may not be able to be broken down into rules. It may just be straight data. The very natural division is to ask for an understanding of anatomy and plasticity rules, which jointly may allow understanding how uncompressible stimuli convert into computation. This could be an analogy to machine learning, where architectures along with learning rules and loss functions give rise to relevant computation. History is full of seemingly impossible things that ended up being possible. It may thus eventually be possible to meaningfully understand a network trained on ImageNet. Importantly, there can be no doubt that doing so is arbitrarily easier than understanding a human brain. After all, for a network trained on ImageNet, we have all the information and can run any experiment we might possibly want to. We thus may want to try and start trying to understand such networks. In tight analogy with microcompressors, despite a thriving community aiming at understanding trained neural networks, there are worries about general feasibility. It is possible that real brains have aspects, strong modularity, approximate linearity, or high noise that make them easier to understand the artificial neural networks, in which case we should be precise about which factors make the task doable. Alternatively, it may be impossible to meaningfully understand a network after training on a complex task, and we may want to start looking for ways of proving that. Or human beings can never understand such a network, but potentially superhuman entities, those built by future high technologies, may be able to understand it. In any of these cases, neuroscience should be informed by this consideration of a lot of approaches currently deployed to understand brains may be rather transparently unable to deliver the results neuroscientists are looking for. The popular approaches used to study brains can readily be focused on studying the nature components as opposed to the nurture components. Behaviorally, we may ask how learning changes the choice of actions. When we study representations, we can ask which loss functions, architecture, and learning dynamics would have given rise to the measured representations. Alternatively, we may ask about the representations as learning signals. When we study connectomics, we can focus on the large-scale anatomy in circuits motifs, which likely are genetically specified, instead of which exact neuron connects to which other exact neuron, which is likely to be learned. Perturbation approaches such as optogenetics can be focused on perturbing the signals that matter for learning. Even within molecular research, we may focus on the cascades that set up the computation, synaptic plasticity, versus those involved in how the computation per se. Instead of asking how the brain works, we should arguably ask how it learns to work. Okay, thanks for tuning in. Hope people are active in the chat. I'll read through the chat later. I haven't really been checking the chat much because mainly I wanted to present information. So this next paper is really good. Anyone who's been following me, should hopefully is going to start seeing this stuff really coming together. And so 2017 in Neuron Review, Neuroscience-Inspired Artificial Intelligence, Hassabis, Kumaran, Summerfield, and Botvinnik. And I think these are the people involved in DeepMind. Some of them are the major players and owners of DeepMind. The field of neuroscience and artificial intelligence have a long and intertwined history. In most recent times, however, communication and collaboration between the two fields has become less commonplace. In this article, we argue that better understanding biological brains could play a vital role in building intelligent machines. We survey historical interactions between the AI and neuroscience fields and emphasize current advances in AI that have been inspired by the study of neural computation in humans and other animals. We conclude by highlighting shared themes that may be key for advancing future research in both fields. In recent years, rapid progress has been made in the related field of neuroscience and artificial intelligence. At the dawn of the computer age, work on AI was inextricably intertwined with neuroscience and psychology, and many of the earlier pioneers straddled both fields, with collaboration between these disciplines proving highly effective. However, more recently, the interaction has become much less commonplace as both subjects have grown enormously in complexity and disciplinary boundaries have solidified. In the review, we argue that the critical and ongoing importance of neuroscience in generating ideas that will accelerate and guide AI research. We begin with the premise that building human-level general AI or Turing powerful intelligent systems is a daunting task because the search space of possible solutions is vast and likely only very sparsely populated. We argue that this therefore underscores the utility of scrutinizing the inner workings of the human brain, the only existing proof that such an intelligence is even possible. Studying animal cognition and its neural implications also has a vital role to play, as it can provide a window into the various important aspects of higher level general intelligence. The benefit to developing AI of closely examined biological intelligence are twofold. First, neuroscience provides a rich source of inspiration for new types of algorithms and architectures independent of the complementary to the mathematical and logical-based methods and ideas that have largely dominated traditional approaches to AI. For example, where new facet of biological computation found to be critical to supporting a cognitive function, then we would consider it an excellent candidate for incorporating into artificial systems. Second, neuroscience can provide a validation of AI techniques that already exist. If a known algorithm is subsequently found to be implemented in the brain, then that is strong support for its plausibility as an integral component of overall general intelligence system. Such clues can be critical to the long-term research program when determining where to allocate resources most productively. For example, if an algorithm is not quite attaining the level of performance required or expected, but we observe it is core to the functioning of the brain, then we can surmise that redoubled engineering efforts geared to making it work in artificial systems are likely to pay off. Of course, from a practical standpoint of building an AI system, we need not slavishly enforce adherence to biological plausibility. For an engineering perspective, what works is ultimately all that matters. For our purposes, the biological plausibility is a guide, not a strict requirement. What we are interested in is a system's neuroscience level understanding of the brain, namely the algorithms, architectures, functions, and representations it utilizes. This roughly corresponds to the top two levels of the three levels of analysis that Marr famously stated are required to understand any complex biological system: the goals of the systems, the computational level, and the processes and computations that realize the goal, the algorithmic level. The precise mechanisms by which this is physically realized in a biological substrate are less relevant here. Note, this is where our approach to neuroscience-inspired AI differs from other initiatives such as the Blue Brain Project or the field of neuromorphic computing systems, which attempt to closely mimic or directly reverse engineer the specifics of neural circuits, even with different goals in mind. By focusing on the computational algorithmic levels, we gain transferable insight into the general mechanisms of brain function while leaving room to accommodate the distinctive opportunities and challenges that arise when building intelligent machines in silico. The following sections unpack these points by considering the past, present, and future of the AI neuroscience interface. Before beginning, we offer a clarification. Throughout this article, we employ the terms neuroscience and AI. We use these terms in the widest possible sense. When we say neuroscience, we mean to include all the fields that are involved in the study of the brain, the behaviors that it generates, and the mechanisms by which it does so, including cognitive neuroscience, systems neuroscience, and psychology. When we say I, we mean all the work in machine learning, statistics, and AI research that aims to build intelligent machines. We begin by considering the origins of the two fields that are pivotal for current AI research: deep learning and reinforcement learning, both of which took root in ideas from neuroscience. We then turn to the current state of play in AI research, noting many cases where inspiration has been drawn, sometimes without explicit acknowledgement, from concepts and findings in neuroscience. In this section, we particularly emphasize instances where we have combined deep learning with other approaches from across machine learning, such as reinforcement learning, Monte Carlo tree search, or techniques involving an external content addressable memory. Next, we consider the potential for neuroscience to support future AI research, looking both at the most likely research challenges and some emerging neuroscience-inspired AI techniques. While our main focus will be on the potential for neuroscience to benefit AI, our final section will briefly consider the ways in which AI may be helpful to neuroscience and the broader potential for synergistic interactions between the two fields. The past, deep learning. As detailed in a number of recent reviews, AI has been revolutionized over the past few years by dramatic advances in neural network or deep learning methods. As the moniker neural network might suggest, the origin of these AI methods lie directly In neuroscience in the 1940s, investigations of neural computation began with the construction of artificial neural networks that could compute logic functions. Not long after, other proposed mechanisms by which networks of neurons might learn incrementally via supervised feedback or efficiency encode environmental statistics in an unsupervised fashion. These mechanisms opened up the field of artificial neural network research, and they continue to provide the foundation for the contemporary research on deep learning. Not long after this pioneering work, the development of the backpropagation algorithm allowed learning to occur in networks composed of multiple layers. Notably, the implications of this method for understanding intelligence, including AI, were first appreciated by a group of neuroscientists and cognitive scientists working under the banner of parallel distribution processing. At the time, most AI research was focused on building logical processing systems based on serial computation, an approach inspired in part by the notion that human intelligence involves manipulation of symbolic representations. However, there was a growing sense in some quarters that purely symbolic approaches might be too brittle and inflexible to solve complex real-world problems of the kind that humans routinely handle. Instead, a growing foundation of knowledge about the brain seemed to point to a very different direction, highlighting the role of stochastic and highly parallelized information processing. Building on this, the PDP movement proposed that human cognition and behavior emerge from dynamic distributed interactions within networks of simple neuron-like processing units, interactions tuned by learning procedures that adjust system parameters in order to minimize error or maximize reward. Although the PDP approach was at first applied to a relatively small-scale problems, it showed striking success in accounting for a wide range of human behaviors. Along the way, PDP research introduced a diverse collection of ideas that had sustained influence on AI research. For example, current machine translation research exploits the notion that words and sentences can be represented in distributed fashion as vectors, a principle that was already ingrained in early PDP-inspired models of sentence processing. Building on the PDP movement's appeal to biological computation, current state-of-the-art convolution neural networks incorporated several canonical hallmarks of neural computation, including nonlinear transduction, divisive normalization, and maximum-based pooling of inputs. These operations were directly inspired by single-cell recordings from the mammalian visual cortex that revealed how visual input is filtered and pooled in simple and complex cells in area V1. However, current network archetypes replicate the hierarchical organization of mammalian cortical systems with both convergent and divergent information flow in successive nested processing layers, following ideas first advanced in early neural network models of visual processing. In both biological and artificial systems, successive nonlinear computation transforms raw visual input into an increasingly complex set of features, permitting object recognition that is invariant to transformations of pose, illumination, or scale. As the field of deep learning evolved out of PDP research into a core area within AI, it was bolstered by new ideas such as the development of deep belief networks and the introduction of large data sets inspired by research on human language. During this period, it continued to draw key ideas from neuroscience. For example, biological considerations informed the development of successful regularization schemes that support generalization beyond training data. One such scheme in which only a subset of units participated in the processing of a given training example was motivated by the stochasticity that is inherent in biological systems populated by neurons that fire with Poisson-like statistics. Here and elsewhere, neuroscience has provided initial guidance toward architectural and algorithmic constraint that lead to successful neural network applications for AI. Reinforcement learning. Alongside its important role in the development of deep learning, neuroscience was also instrumental in erecting a second pillar of contemporary AI, stimulating the emergence of the field of reinforcement learning. Reinforcement methods address the problem of how to maximize future reward by mapping states in the environment to actions, and are among the most widely used tools in AI research. Although it's not widely appreciated among AI researchers, reinforcement learning methods were originally inspired by research into animal learning. In particular, development temporal difference methods is a critical component of many reinforcement learning models, was inextricably intertwined with research into animal behavior and conditioning experiments. Temporal difference methods are real-time models that learn from differences between temporary successive predictions rather than having to wait for the actual reward is delivered. Of particular relevance was an effect called second-order conditioning, where effective significance is conference on a conditional stimulus through association with another conditional stimulus rather than directly via association with unconditioned stimulus. Temporal difference learning provides a natural explanation for second-order conditioning, and indeed has gone on to explain a much wider range of findings from neuroscience as we discussed below. Here's in the case of deep learning investigations initially inspired by observations from neuroscience led to further developments that have strongly shaped the direction of AI research from the neuroscience-informed origins. PD methods and related techniques have gone on to supply the core technology for recent advances in AI, ranging from robotic control to expert play in backgammon and Go. Most notable through Pavlovian dogs. So the present. Reading the contemporary AI literature, one gains the impression that the earlier engagement with neuroscience has diminished. However, one scratches the surface, one can uncover many cases in which recent developments have been inspired and guided by neuroscientific considerations. Here we look at 4 specific examples. Attention. The brain does not learn by implementing a single global optimization principle within a uniform and undifferentiated neural network. Rather, biological brains are modular with distinct but interacting subsystems underpinning key functions such as memory, language, and cognitive control. The insight from neuroscience has been imported, often in an unspoken way, into many areas of current AI. One illustrative example is a recent AI work on attention. Up until quite lately, most convoluted neural network models work directly on entire images or video frames with equal priority given to all image pixels at the earliest stage of processing. The primate visual system works differently. Rather than processing all input in parallel, visual attention shifts strategically among locations and objects, centering processing resources and representational coordinates on a series of regions in turn. Detailed neurocomputational models have shown how this piecemeal approach benefits behavior by prioritizing and isolating the information that is relevant at any given moment. As such, attentional mechanisms have been a source of inspiration for AI architectures that take glimpses of the input image at each step, update internal state representations, and then select the next location to sample. One such network was able to use this selective attentional mechanism to ignore irrelevant objects in a scene, allowing it to perform well into challenging object classification tasks in the presence of clutter. Further, the attentional mechanisms allowed the computational cost to scale favorably with the size of the input image. Extensions of this approach were subsequently shown to produce impressive performance at difficult multi-object recognition tasks, outperforming conventional convolutional neural networks that process the entirety of the image, both in terms of accuracy and computational efficiency, as well as enhancing image-to-caption generation. While attention is typically thought of as an orienting mechanism for perception, its spotlight can also be focused internally towards the contents of memory. The idea or recent focus in neuroscience studies has also inspired work in AI. In some architectures, attentional mechanisms have been used to select information to be read out from the internal memory of the network. This has helped provide recent successes in machine translations and led to important advances on memory and reasoning tasks. These architectures offer a novel implementation of content addressable retrieval, which was itself a concept originally introduced to AI from neuroscience. One further area of AI where attention mechanisms have recently proven useful focuses on generative model systems that learn to synthesize or imagine images or other kinds of data that mimic the structure of examples presented during training. Deep generative models have recently shown striking successes in producing synthetic outputs that capture the form and structure of real visual scenes via the incorporation of attention-like mechanism. For example, in one state-of-the-art generative model known as Draw, attention allows the system to build up an image incrementally, attending to one portion of a mental canvas at a time. Episodic memory. Canonical theme in neuroscience is that the intelligent behavior relies on multiple memory systems. These will include not only reinforcement-based mechanisms which allow the value of stimuli and action to be learned incrementally and through repeated experience, but also instance-based mechanisms which allow experience to be encoded rapidly in one shot in a content-addressable store. The latter form of memory, known as episodic memory, is most often associated with circuits in the medial temporal lobe, prominently including the hippocampus. One recent breakthrough in AI has been the successful integration of reinforcement learning with deep learning. For example, the DeepQ network exhibits expert play on Atari 2600 games by learning to transform a vector of image pixels into a policy for selecting actions, like the joystick movements. One key ingredient in DeepQ network, is experience replay, whereby the network stores a subset of the training data in an instant-based way and then replays it offline, learning anew from successes or failures that occurred in the past. Experience replay is critical to maximizing data efficiency, avoids destabilizing effects of learning from the consecutive correlated experiences, and allows the network to learn a value function even in complex, highly structured sequential environments such as video games. So let me read this here. Parallels between AI systems and neural modes of behavior. So here you have attention, schematic of recurring attention model. A here. Given an input image in foveal location, the glimpse sensor extracts a multiple resolution retinal representation. This is the input to a glimpse network, which reproduces a representation that is passed to the long short-term memory core, which defines the next location to attend to and classification decision. And then B, the episodic control. Schematics of complementary systems, learning systems, episodic control, top non-parametric fast learning hippocampal systems, and parametric slow learning neocortical systems. Hippocampus instance-based systems support rapid behavioral adjustments and experience replay, which supports interleaved training on deep neural networks or neocortex. On the bottom, you see the episodic control game states are shown with buffers, one in each possible action, together with the highest return experience from the state. When experiencing a new state, the policy is determined by averaging the Q value across K nearest neighbors in each action buffer and selecting the action with the highest expected return. So how the understanding of the information could lead to a joystick motion there, similar to based on models of how the brain might work. And we're going to get to these two, the central executive and the cascade model. I'll read through these now. Illustrations of the parallels between macroscopic organizations of models of working memory and the differential neural computer. The neural Turing machine, the network controller, is analogous to the central executive and attends, reads, writes to an external memory matrix. Architecture is shown performing a copy task. So it's here in C. And then D is going to be the cascade model. Illusions of parallel between the neurobiological models of a synaptic consolidation of the elastic weight consolidation algorithm. So you have two photon structure image dating showing learning-related increase in size of dendrites, each corresponding approximately to a single excitatory synapse that persists for months. In the middle of the schematic cascade model of synaptic consolidation. Binary synapses transition between metaplastic states, which are more or less plastic, as a function of prior potentiation depression events. The right panel is the schematic of elastic weight consolidation algorithm. After training on the first task, network parameters are optimized for good performance. The single weight elastic weight consolidation implements a constraint analogous to a spring that anchors weights to the previously found solution when training a new task, with the stiffness of the spring proportional to the importance of the parameter to the task. Very interesting. So back to the episodic memory control. Critically experienced replay was directed and inspired by theories that seek to understand how the multiple memory systems in the mammalian brain might interact. According to a prominent view, animal learning is supported by parallel and complementary learning systems in the hippocampus and neocortex. The hippocampus acts to encode novel information after a single exposure, but this information is gradually consolidated to the neocortex in sleep or resting periods that are interleaved with periods of activity. The consolidation is accompanied by replay in the hippocampus and neocortex, which is observed as a reinstatement of the structured patterns of neural activity that accompanied the learning event. This theory was originally proposed as a solution to the well-known problem that in conventional neural networks, correlated exposure to sequential task setting leads to mutual interference among policies, resulting in catastrophic forgetting of one task as a new one is learned. The replay buffer in DQN might thus be thought of as a very primitive hippocampus, permitting complementary learning in silico, much as proposed for biological brains. Later work showed the benefits of experience replay in DQN are enhanced when replay of the highly rewarding events is prioritized, just as hippocampal replay seems to favor events that lead to high levels of reinforcement. Experience is stored in memory buffer can not only be used to gradually adjust the parameter of a deep network towards an optimal policy, such as DQN, but can also support rapid behavioral change based on individual experience. Indeed, theoretical neurosciences argued for the potential benefits of episodic control, whereby rewarded action sequences can be internally reenacted from a rapidly unsustainable memory store implemented in the biological case in the hippocampus. Further, normative accounts show that episodic control is particularly advantageous over other learning mechanisms when limited experience of the environment has been obtained. Recent AI research has drawn on these ideas to overcome the slow learning characteristics of deep reinforcement learning networks, developing architectures that implement episodic control. These networks store specific experiences, actions, and reward outcomes associated with and select new actions based on the similarity between the current situational input and the previous events stored in memory, taking the reward associated with those previous events into account. As predicted from the initial neuroscience-based work, artificial agents employing episodic control showed striking gains in performance over deep reinforcement learning networks, particularly early on in learning. Further, they're able to achieve success on tasks that depend heavily on one-shot learning, where typically a deep reinforcement learning architecture fails. More of episodic-like memory systems more generally have shown considerable promise in allowing new concepts to be learned rapidly based on only a few examples. In the future, it will be interesting to harness the benefits of rapid episodic memory and more traditional incremental learning in architectures that incorporate both of the components within an interacting framework that mirrors the complementary learning systems in mammalian brain. We discuss these future perspectives below in more detail later in Imagination and Planning. Working memory. Human intelligence is characterized by a remarkable ability to maintain and manipulate information with an active store known as working memory, which is thought to be instantiated within the prefrontal cortex in interconnected areas. Classic cognitive theories suggest that this functional depends on the interactions between the central controller, the executive, and separate domains memory buffers. AI research has drawn inspiration from these models by building architectures that explicitly maintain information over time. Historically, such efforts began with the introduction of recurrent neural network architectures displaying attractive dynamics and rich sequential behavior, work directly inspired by neuroscience. This work enabled later more detailed modeling of the human working memory, but it also laid the foundation for further technical innovations that have proved pivotal for AI research. In particular, one can see close parallels between the learning dynamics in these early neuroscience-inspired networks and those in long-term short memory networks, which subsequently achieved state-of-the-art performance across a variety of domains. The LTSMs allow information to be gated into a fixed activity state and maintained until appropriate output is required. Variants of this type of network have shown some striking behaviors in challenging domains, such as learning to respond to queries about the latent state of variables after training on computer code. In ordinary LSTM networks, their functions as sequences, control, and memory storage are closely intertwined. This contrasts with classic models of human working memory, which, as mentioned above, separate these two. The neuroscience-based schema has recently inspired more complex AI architectures where control and storage are supported by distinct modules. For example, the differential neural computer involves a neural network controller that attends to and reads writes from an external memory matrix. The externalization allows the network controller to learn from scratch to perform a wide range of complex memory and reasoning tasks that currently elude LSTM, such as finding the shortest path through a graph-like structure, such as a subway map, or manipulating blocks in a variant of a Tower-Hanoi task. These types of problems were previously argued to depend exclusively on symbol processing and variable binding and therefore beyond the purview of neural networks. Of note, although both LSTMs and the DNC are described here in the context of working memory, they have the potential to maintain information over many thousands of training cycles, and so may thus be suited to longer-term forms of memory, such as retaining and understanding the contents of a book. Continual learning. Intelligent agents must be able to learn and remember many different tasks that are encountered over multiple timescales. Both biological and artificial agents must thus have a capacity for continual learning, that is, an ability to master new tasks without forgetting how to perform prior tasks. While animals appear relatively adept at continual learning, neural networks suffer from the problem of catastrophic forgetting. This occurs as the network parameters shift toward the optimal state for performing the second of two successive tasks, overriding the configuration that allowed them to perform the first. Given the importance of continual learning, this liability of neural networks remains a significant challenge for the development of AI. In neuroscience, advanced neuroimaging techniques now allow dynamic in vivo visualization of the structure and function of dendritic spines during learning the spatial scale of single synapses. This approach can be used to study neocortical plasticity during continual learning. There's emerging evidence for specialized mechanisms that protect knowledge about previous tasks from interference during learning of a new task. These include a decreased synaptic lability, lower rates of plasticity, in proportion of strengthened synapses mediated by enlargements to dendritic spines that persist despite learning of other tasks. These changes are associated with retention of task performance over several months, and indeed, if they are erased with synaptic optogenetics, this leads to forgetting of the task. These empirical insights are consistent with theoretical models that suggest that memories can be protected from interference through synapses that transition because of cascaded states with different levels of plasticity. Therefore, together, these findings from neuroscience have inspired the development of AI algorithms that address the challenges of continual learning in deep networks by implementation of a form of elastic weight consolidation, which acts by slowing down learning in a subset of network weights identified as important to previous tasks, thereby anchoring these parameters to previously found solutions. This allows multiple tasks to be learned without an increase in network capacity, with weights shared efficiently between tasks with related structure. In this way, the EWC algorithm allows deep reinforcement learning networks to support continual learning at large scale. Future. In AI, the pace of research has been remarkable. Artificial systems now match human performance in challenging object recognition tasks and outperform expert humans in dynamic adversarial environments such as Atari video games. The ancient board game Go, the imperfect information games such as heads-up poker, machines can automatically generate synthetic natural images and simulations of human speech that are almost indistinguishable from real-world counterparts, translate between multiple languages, and create neural art in the style of well-known painters. However, much work is still needed to bridge the gap between machine and human-level intelligence. In working towards closing this gap, we believe ideas from neuroscience will become increasingly indispensable. In neuroscience, the advent of new tools for brain imaging and genetic bioengineering have begun to offer a detailed characterization of the computations occurring in neural networks, promising a revolution of our understanding of the mammalian brain function. The relevance of neuroscience, both as a roadmap for the AI research agenda and as a source of computational tools, is particularly salient in the following key areas. Intuitive understanding of the physical world. Reason perspectives emphasize the key ingredients of human intelligence that are already well developed in the human brain. Infants, but lacking in most AI systems. Among these capacities are knowledge of core concepts relating to the physical world, such as space, number, and objectness, which allow people to construct compositional mental models that can guide inference and prediction. AI research has begun to explore methods for addressing this challenge. For example, novel neural network architecture has been developed that interpret and reason about scenes in a human-like way by decomposing them into individual objects and their relations. In some cases, this has resulted in human-level performance on challenging reasoning tasks. In other work, deep reinforcement learning has been used to capture the processes by which children gain common sense understanding of the world through interactive experiments. Related deep generative models have been developed that are able to construct rich object models from raw sensory inputs. These leverage constraints first identified in neuroscience, such as redundancy reduction, which encourage the emergence of disentangled representations of independent factors such as shape and position. Importantly, the latent representations learned by such generative models exhibit compositional properties supporting flexible transfer to novel tasks. In the caption associated Figure 2, we provide more detailed information about these networks. Efficient learning. Human cognition is distinguished by its ability to rapidly learn about new concepts from only a handful of examples, leveraging prior knowledge to enable flexible inductive inferences. In order to highlight this human ability as a challenge for AI, Lake and colleagues recently proposed a characters challenge. Here, an observer must distinguish novel instances of an unfamiliar handwritten character from other similar items after viewing only a single exemplar. Humans can perform this task well, but is difficult for classical AI systems. Encouragingly, recent AI algorithms have begun to make progress on the task like the characters challenge through both structured probabilistic models and deep generative models based on the above-mentioned draw model. Both classes of systems can make inferences about new concepts despite a poverty of data and generate new samples from a single example concept. Further, recent AI research has developed networks that learn to learn, acquire knowledge on new tasks by leveraging prior experience with related problems to support one-shot concept learning and accelerating learning in reinforcement learning tasks. Once again, this builds on the concept from neuroscience. Learning to learn was first explored in studies of animal learning and has subsequently been studied in developmental psychology. Transfer learning. Humans also excel at generalizing and transferring generalized knowledge gained in one context to novel, previously unseen domains. For example, a human who could drive a car, use a laptop computer, or a chair a committee meeting is usually able to act effectively when confronting with an unfamiliar vehicle, operating system, or social situation. Progress is being made in developing AI architectures capable of exhibiting strong generalizations or transfer, for example, by enabling zero-shot inferences about novel shapes outside the training distribution based on compositional representations. Others have shown that a new class of architecture known as progressive network can leverage knowledge gained on one video game to learn rapidly in another, promising the sort of far transfer that is characteristic on human skill acquisition. Progressive networks have also been successfully employed to transfer knowledge for a simulated robotic environment to a real robot arm, massively reducing the training time required in the real world. Intriguingly, the proposed architecture bears some resemblance to the successful computational model of sequential task learning in humans. In the neuroscience literature, one hallmark of transfer learning has been the ability to reason rationally, and AI researchers have also begun to make progress in building deep networks that address problems of this nature, for example, by solving visual analogies. More generally, however, how humans and other animals achieve this sort of high-level transfer learning is unknown and remains a relatively unexplored topic in neuroscience. New advances on this front could provide critical insight to spur AI research toward the goal of lifelong learning in agents, and we encourage neuroscientists to engage more deeply with this question. At the level of neurocoding, the kind of transfer of abstract structured knowledge may rely on the formation of conceptual representations that are invariant to the objects, individuals, or scene elements that populate a sensory domain, but code instead for abstract relational information among patterns of inputs. However, we currently lack direct evidence for the existence of such codes in the mammalian brain. Nevertheless, one recent report made the very interesting claim that neural codes thought to be important in the representation of allocentric map-like spaces might be critical for abstract reasoning in more general domains. In the mammalian entorhinal cortex, cells encode the geometry of allocentric space with a periodic grid code, which receptive fields that tile the local space in a hexagonal pattern. Grid codes may be excellent candidates for organizing conceptual knowledge because they allow state spaces to decompose efficiently in a way that could support discovery of subgoals and hierarchical planning. Using functioning neural imaging, the research provides evidence for the existence of such codes. While the humans performed an abstract categorization task supporting the view that periodic encoding is a generalized hallmark of human knowledge organization. However, much further work is required to substantiate this interesting claim. So let's see the visualization here. I got the 4 models, examples of recent AI systems that are inspired by neuroscience. So first one here, intuitive physics knowledge, illustration of the ability of the interaction network to reason and make predictions about a physical interaction between objects in the bouncing ball problem and spaceship problem. The neural network takes an input objects and their relationships and accurately simulates their trajectories by modeling collisions, gravitation forces, effectively acting as a learned physics engine. Then scene understanding through structured generative models, the iterative inference in variation autoencoder architecture, the recurrent network attends to one object at a time, infers its attribute, and performs the appropriate number of inference steps for each input image. Scenes are described in terms of groups of latent variables that specify presence, absence, properties such as position, shape, inference network, and the generator network, which produce reconstruct image. In the illustrator of the iterative inference in multiple MINST images, green indicates the first step and red the second step. The inference about the position shape of the multiple objects in realistic scene. Note the inference is accurate, and hence it is difficult to distinguish inferred positions, latent representations, and network speed learning on downstream tasks. So this is the representation B here, the three different things. Image processing. And you see C and D. So unsupervised learning, or object properties is shown. Left schematic illustrating learning of a disentangled factors of sensory input by deep generative model, whose representations can speed learning on downstream tasks as compared to relatively entangled representations learned by typical deep networks. On the right, the right panel illustrates the latent representations of the variational autoencoder. Latent units encoding for factors of variation such as object position, rotating, and scale are shown by effect of independently changing the activity of one latent unit. Such networks can learn intuitive concepts such as objectness, being able to support zero-shot transfer. And the last two, D and E, one-shot generation and deep sequence generative models is shown. Deep generative models specify a causal process for generating the observed data using a hierarchy of latent variables with attention mechanisms supporting sequential inferences. Illustrated are generated samples of the model conditioned on a single novel character from held out alphabet from the Omniglot dataset, demonstrating abilities that mirror human abilities to generalize from a single concept. And the last one, E, imagination of a realistic environment in deep networks is shown. Generated left and right, the generated in real frames from procedural mazes produced by an action conditioned recurrent network model. Okay, so thanks for sticking with me, those still here, and finish up here. Last few pages. Imagination and planning. Despite their strong performance of goal-directed tasks, deep reinforcement learning systems such as DQN operate mostly in a reactive way, learning the mapping from perceptual inputs to actions that maximize future value. This model-free reinforcement learning is computationally inexpensive, but suffers from two major drawbacks: is relatively data inefficient, requiring large amounts of experience to derive accurate estimates, and is inflexible, being insensitive to changes in the value of outcomes. By contrast, humans can more flexibly select actions based on forecast of long-term future outcomes through simulation-based planning, which uses predictions generated from an internal model of the environment learned through experience. Moreover, planning is not a uniquely human capacity. For example, when catching food, scrub jays consider the future conditions under which is likely to be recovered, and rats use a cognitive map when navigating, allowing inductive inferences during wayfinding and facilitating one-shot learning behaviors in maze-like environments. Of course, this point has not been lost on AI researchers. Indeed, early planning algorithms such as DINA were inspired by theories that emphasize the importance of mental models and generating hypothetical experiences useful for human learning. By now, a large volume of literature exists on AI planning techniques, including model-based reinforcement learning methods, which seek to implement the forecast-based method of action selection. Furthermore, simulation-based planning, particularly Monte Carlo tree search methods, which use forward search to update a value function and/or policy, played a key role in recent work in which deep reinforcement learning attained expert-level performance in the game of Go. AI research on planning, however, has yet to capture some of the key characteristics that give human planning abilities their power. In particular, we suggest that a general solution to this problem will require understanding how rich internal models, which in practice will have to be approximate but sufficiently accurate to support planning, can be learned through experience without strong priors being handcuffed to the network by the experimenter. We also argue that AI research will benefit from a close reading of the related literature on how humans imagine possible scenarios, envision the future, and carry out simulation-based planning, functions that depend on a common neural substrate in the hippocampus. Although imagination is intrinsically subjective, unobservable quality, we have to reason to believe that it has a conserved role in simulation-based planning across species. For example, when paused at a choice point, ripples of neural activity in a rat hippocampus resemble those observed during subsequent navigation of the available trajectory, as if the animal were imagining each possible alternative. Further, recent work has suggested a similar process during non-spatial planning in humans. We have discussed above the ways in which the introduction of mechanisms that replay and learn online from past experiences can improve the performance of deep reinforcement learning, such as DQN. Some encouraging initial progress towards simulation-based planning has been made using deep generative models. In particular, recent work has introduced new architectures that have the capacity to generate temporal consistent sequences of generated samples that reflect the geometric layout of newly experienced realistic environments, providing a parallel to the function of the hippocampus and binding together multiple components to create an imagined experience that is spatially and temporally coherent. Deep generative models thus show the potential to capture the rich dynamics of complex realistic environments, but using these models for simulation-based planning and agents remains a challenge for future work. Insights from neuroscience may provide guidance that facilitates the integration and stimulus with controls. An emerging picture from the neuroscience research suggests that the hippocampus support planning by instantiating an internal model of the environment with goal contingent evaluation and simulated outcomes occurring in areas downstream of the hippocampus, such as the alpha-frontal cortex or the striatum. Notably, however, the mechanisms that guide the rolling forward of internal model of the environment of the hippocampus remain uncertain and merit future scrutiny. One possibility is that this process is initiated by prefrontal cortex through interactions with the hippocampus. Indeed, the notion has distinct parallels with proposals from AI research that a separate controller interacts with an internal model of the environment in a bidirectional fashion, querying the model based on task-relevant goals and receiving predicted stimulated states and input. Further, recent efforts to develop agents have employed architectures that instantiate a separation between controller and environmental model to affect simulation-based planning and problems involving the interaction between physical objects. In enhancing agent capabilities in simulation-based planning, it will also be important to consider other salient properties of this process in humans. Research into human imagination emphasizes its constructive nature, with humans able to construct fictitious mental scenarios by recombining familiar elements in novel ways, necessitating compositional disentangled representations in the form present in certain generative models. This fits well into the notion that planning in humans involves efficient representations that support generalizations and transfer, so that plans forged on one setting can be leveraged in novel environments that share structure. Further, planning and mental simulation. Humans are jumpy, bridging multiple temporal scales at a time. For example, humans seem to plan hierarchically by considering in parallel terminal solutions, interim choice points, and piecemeal steps towards a goal. We think that ultimately these flexible combinatorial aspects of planning will form a critical underpinning for what perhaps the hardest challenge of AI to research. To build an agent that can plan hierarchically is truly creative and can generate solutions to challenges that currently elude even the human mind. Virtual brain analytics. One rather different way in which neuroscience may serve AI is by furnishing new analytic tools for understanding computation in AI systems. Due to their complexity, these products of AI research often remain black boxes. We understand only poorly the nature of the computations that occur or representations that are formed during learning of complex tasks. However, by applying tools from neuroscience to AI systems, synthetic equivalents of single-cell recording, neuroimaging, and lesion techniques, we can gain insight into the key drivers of successful learning in AI research and increase the interpretability of these systems. We call this the virtual brain analytics. Recent work has made some progress along these lines. For example, visualizing brain states through dimensionality reduction is a commonplace in neuroscience and has been recently applied to neural networks. Receptive field mapping, another standard tool in neuroscience, allows AI researchers to determine the response properties of units in a neural network. One interesting application of this approach of AI is known as activity maximization, in which networks learn to generate synthetic images by maximizing the activity of certain classes of units. Elsewhere, neuroscience-inspired analysis of linearized networks have uncovered important principles that may be of general benefit in optimizing learning these networks and understanding the benefits of network depth and representational structure. While this initial process is encouraging, more work is needed. It remains difficult to characterize the functioning of complex architectures such as networks with external memory. Nevertheless, AI researchers are in the unique position of having ground through truth knowledge of all components of the system together, with the potential to causally manipulate individual elements, an enviable scenario for the perspective of experimental neuroscience. As such, we encourage AI researchers to use approaches from neuroscience to explore properties of network architectures and agents through analysis, visualization, causal manipulation, not forgetting the need to carefully designed hypothesis-driven experiments. We think that virtual brain analytics is likely to be an increasingly integral part of the pipeline of algorithmic development as the complexity of architecture increases. From AI to neuroscience. Thus far, our review has focused primarily on the role of neuroscience in accelerating AI research rather than vice versa. Historically, however, the flow of information between neuroscience and AI has been reciprocal. Machine learning techniques have transformed the analysis of neuroimage data sets. For example, the multivariate analysis of fMRI and magnet MEG data with promise for expediting connectomic analysis. Among other techniques, going further, we believe that building intelligent algorithms has the potential to offer new ideas about the underpinnings of intelligence in the brains of humans and other animals. In particular, psychologists in neuroscience often have only quite vague notions of the mechanisms that underlie the concepts of the study. AI research can help by formalizing these concepts into qualitative language and offering insights into the necessity and sufficiency for intelligent behavior. A key illustration of this potential is provided by reinforcement learning. After ideas from animal psychology helped to give birth to reinforcement learning research, key concepts from the latter fed back to inform neuroscience, in particular the profile of neural signals observed in midbrain dopaminergic neurons in conditioning paradigms was found to bear a striking resemblance to TD-generated predicting errors, providing neural evidence that the brain implements a form of TD learning. This overall narrative arc provides an excellent illustration of how the exchange of ideas between AI and neuroscience can create a virtuous circle, advancing the objectives of both fields. In another domain, work focused on enhancing the performance of convoluted neural networks has also yielded new insights into the nature of neural representations in high-level visual areas. For example, one group of systematically compared the ability of more than 30 network architectures from AI to explain the structure of neural representations observed in the ventral visual stream of humans and monkeys, finding favorable evidence of deep supervised networks. Further, these deep convolution network architectures offer a computational account of recent neurophysiological data demonstrating that the coding of category orthogonal properties of objects like position and size actually increase as one progresses higher up the ventral visual system. While these findings are far from definitive as yet, it shows how state-of-the-art neural networks from AI can be used as a plausible simulacra of biological brains, potentially providing detailed explanations of the computations occurring therein. Relatedly, properties of the LSTM architecture has provided key insights that motivated the development of working memory models that afford gating-based maintenance of task-relevant information in the prefrontal cortex. We also highlighted two recent strands of AI research that may motivate new research in neuroscience. First, neural networks with external memory typically allow the controller to iteratively query and hop through the contents of memory. Thus, mechanism is critical for reasoning over multiple supporting input statements that relate to a particular query. Previous proposals in neuroscience have argued for a similar mechanism in human cognition, but any potential neural substrates potentially in the hippocampus remain to be described. Second recent work highlights the potential benefits of meta-reinforcement learning, where reinforcement learning is used to optimize the weights of a recurrent network, such as the latter is able to implement a second emergent reinforcement learning algorithm that is able to learn faster than the original. Intriguingly, these ideas connect with a growing neuroscience literature indicating a role for the prefrontal cortex in reinforcement learning alongside more established dopamine-based mechanisms. Specifically, they indicate how a relatively slow-learning dopaminergic reinforcement learning algorithm may support the emergence of a freestanding reinforcement learning algorithm instantiated with the recurrent activity dynamics of the prefrontal cortex. And Doooovid is going to read a paper on that hopefully soon. Insights from the AI research also are providing novel perspectives on how the brain might implement an algorithmic parallel to backpropagation, the key mechanism that allows weights within multiple layers of hierarchical networks to be optimized toward an objective function. Backpropagation offers a powerful solution to the problem of credit assignment within deep networks, allowing efficient representations to be learned from the high dimensionality data. However, until recently, several aspects of the backpropagation algorithm were viewed to be biologically implausible. One important factor is that backpropagation has typically been thought to require perfectly symmetric feedback and feed-forward connectivity, a profile that is not observed in mammalian brains. Recent work, however, has demonstrated that this constraint can in fact be relaxed. Random backward connections, even when held fixed throughout network training, are sufficient to allow the backpropagation algorithm to function effectively through a process whereby adjustments in the forward weight allow backward projections to transmit useful teaching signals. Second core objection to the biological plausibility of backward propagation is the weight updates in multi-layered networks require access to information that is non-local, like error signals generated by units many layers downstream. In contrast, plasticity in biological synapses depends primarily on local information, pre- and post-synaptic neuronal activity. AI research has begun to address this fundamental issue. In particular, recent work has shown that hierarchical autoencoder networks and energy-based networks, models that have strong connections to theoretical neuroscience ideas about predictive coding, are capable of approximating the backpropagation algorithm based on the weight updates that involve purely local information. Indeed, concrete connections have been drawn between learning in such networks and spike timing dependent plasticity, a Hebbian mechanism instantiated widely across the brain. A different class of local learning rules has been shown to allow hierarchical supervised networks to generate high-level invariants characterized of biological systems, including mirror symmetric tuning to physical symmetric stimuli such as faces. Taken together, recent AI research offers the promise of discovering mechanisms by which the brain might implement algorithms within the functionality of backpropagation. Moreover, these developments illustrate the potential for synergistic interaction between AI and neuroscience. Research aimed to develop biologically plausible forms of backpropagation have also been motivated by the search for alternative learning algorithms. Given the increasingly deep networks used in AI research, factors such as compounding of successive nonlinearities poses challenge for optimization using backpropagation. So in conclusion, in this perspective, we have reviewed some of the many ways by which neuroscience has made fundamental contributions to advancing AI research and argued for its increasing important relevance. In strategizing the future exchanges between the two fields, it is important to appreciate the past contributions of neuroscience to AI have rarely involved a simple transfer of full-fledged solutions that could be directly re-implemented in machines. Rather, neuroscience has typically been useful in a subtler way, stimulating algorithmic level questions about facets of animal learning and intelligence of interest to AI researchers and providing initial leads towards relevant mechanisms. As such, our view is that leveraging insights gained from neuroscience research will expedite progress in AI research, and this will be most effective if AI researchers actively initiate collaboration with neuroscientists to highlight key questions that could be addressed by empirical work. The successful transfer of insight gained from neuroscience to the development of AI algorithms is critically dependent on the interaction between researchers working in both these fields, with insights often developing thought through a continual handing back and forth of ideas between fields. in the future, we hope that the greater collaboration between researchers in neuroscience and AI and the identification of common language between the two fields will permit a virtuous circle whereby researchers is accelerated through shared theoretical insight and common empirical advances. We believe that the quest to develop AI will ultimately also lead to a better understanding of our minds and thought processes. Distilling intelligence into an algorithmic construct and comparing it to the human brain might yield insights into some of the deepest and most enduring mysteries of the mind, such as the nature of creativity, dreams, and perhaps one day even consciousness. Okay, great. So I'm glad I read that paper straight out. At least for my own purposes, handful of people watching. Judas, shalom. Hope people watching gain from this. You can see I have a lot more on chess here. I'm putting the AI stuff. A lot of these don't actually have to do with chess. I also have quite a bit more in the multiple truth area, and then these Ask the Rabbis on the nature of the soul, reincarnation, Goy, slavery. I have stuff on Freemasonry, Vivekananda, Hinduism. But I'm going to focus probably the most on chess and the artificial intelligence and then bring it back. But I'm glad to get a stream out there and connect some of it to the multiple truth hypothesis and exciting the news about AlphaFold, which so thanks everyone for tuning in. Shalom, blessings. Week in review on Church of Entropy's channel later tonight. Join us there. We have some guests. Anyone who sees this and wants to talk more about it, reach out, make a comment. Looking forward to that, and looking forward to producing more research. Also, I think the week after next, I'm going to interview Danishvara Das, who I think is in Croatia. Hare Krishna devotee, maybe originally from Detroit. He's been here. I've met him many times. He also wrote Spiritual Economics, and he wrote this book recently, Divine or Demonic Spiritual Movements and the Enemies Within. So I look forward to hopefully hosting him on my YouTube channel the week after this. Hanukkah is this Friday night. There's going to be a bunch of Hanukkah celebrations, Chabad. I'm not sure if I'm going to be live streaming or with COVID-19, how we're going to handle. So blessings, everybody. Preparations, happy Hanukkah. Multiple truth hypothesis is coming together. Hopefully people see, the deep AlphaFold, and, really appreciate Jennifer's help with the mathematics, and you're just encouraging me, providing a platform to theorize on this. And I think it's paying off for Jennifer also. As you see, she's likely to be coming out with her book soon. So blessings and take care, everyone. Shalom.